Is everything good? You can hear me? Should we start or not yet? Okay. Why is Zoom so slow? I joined the wrong meeting. All good? There's some echo now. Okay, it's gone. Okay, let's get started. All good, right? Okay. So in the last two lectures, we covered storage, flash memory, as well as SSDs. As I mentioned yesterday, these are fascinating topics that you wouldn't get to cover, in my opinion, anywhere else. I have not seen a computer architecture course that covers these things. As I also jokingly mentioned that if you've taken a computer architecture course in many places, they would probably think flash memory doesn't exist. I'm just kidding. Well, that's kind of a joke, but that's true. But if you think about it, these are things. This is also an example of the processor-centric mindset that we have in how we teach computer architecture. If you look at the traditional computer architecture course, it's all about the processor, right? But some of the things that has actually revolutionized computing systems is outside the processor, like flash storage, right? Memory, main memory. These are the components that are really important. And I think we need to change how we deal with our courses across the world if we also want to change the paradigm of computation. It's kind of a chicken and the egg problem, right? People keep thinking processor-centric and they keep generating processor-centric systems, and they cannot break out of the box because they have no idea what's going on outside the processor. It's good to think about that. This is why paradigms are hard to change, right? In some of my recent lectures, I kind of give the example of changing a paradigm is not easy. And if you know about paradigms, I think in my first lecture, I talked about The Structure of Scientific Revolutions by Thomas Kuhn. It's a beautiful book. I'd recommend people to read it. And a lot of people have had difficulty in changing the paradigm, right? For example, people for a very long time thought that sun revolves around the earth. And there was a huge pushback against people who actually tried to prove that earth revolves around the sun, right? The Copernican revolution. It didn't end with Copernicus. It took 200 years. There was a huge investment. And the investment is fueled by education, which may be based on wrong assumptions. People who have vested interest to make people think that sun revolves around the earth. Catholic Church being one of the major examples. And dogma, basically, that people think, because that's how it has been. Like, why change, right? If you remember that book from Raj Jain, it's working okay. We're thinking sun revolves around the earth, and for me it's working okay. For you it's working okay. For how many people it's working okay. Why are you causing problems? See, this is what happens if you try to change the paradigm. You're a problem maker. Or if you try to change things that are that the establishment considers unchangeable, let's say. So it's good to keep that in mind. That's why we take a very different approach in this course. We start with memory, and we're still covering memory. Today, I'm going to cover simulation, actually, which is an important part of memory. But simulation is actually broader than memory. But keep this in mind. I think this is actually, whatever I just said is probably more important than anything else that you can get out of this course. Whenever you go and try to change things, you're going to work against an establishment. And that establishment has vested interest. In this case, it's not the Catholic Church, it's not the dogma, it's not the scientists who strongly believe that sun revolves around the earth for whatever reason, despite all the evidence. In this case, it's vested interest in processor-centric thinking, right? So that's why you don't see flash memory in courses, because, well, that's part of it. The other part of it is people are lazy, right? Why learn about flash memory when you can teach about a 4-stage pipeline, MIPS? That sounds good, right? Not even 5 stages, 4 stages. They used to be happy with 2 stages at some point, and then they decided 5 stages are better. But it doesn't go beyond 5. That's it. Okay. Anyway, let's keep the jokes for now. There are more jokes coming in simulation. Maybe Nisa will give you some jokes related to what she has experienced recently. It's good to experience things. Then you can talk more freely. Okay, so we're going to talk about simulation, which is a fascinating part of a lot of things, actually. Simulation is a very broad field, right? It's not just computer architecture. Many people do simulation. Physicists do simulation. Chemists do simulation. A lot of people, for discovery, they need to do simulation, right? But somehow, in our little world of computer architecture, when you cross the software-hardware boundary, software people think simulation is bad. And I have no idea where they came up with this. I'm going to go against, again, establishment, right? If you go to a software conference and submit a simulation, they say, oh, it's a simulation. Scrap it. Well, everybody does simulation. A lot of discoveries came about because of simulation, right? That's how people actually model the world. Simulation is a modeling tool so that you can gain insight about something so that you can invent something new. So basically, simulation is not bad. Simulation is good. And those software people should be thinking much more open-mindedly, because not everything in the world has to be implemented in software to be useful. I'll start with that. And I think Nisa's story is related to this also, but I have many stories. I'm going to give you one of them later on. You can give it when you talk. Okay, so simulation is actually a tool to enable modeling of things that we cannot maybe completely imitate. I mean, it could be an imitation tool, but the goal is to actually model something so that we can better understand it and design better things. So we're going to talk especially about simulating memory systems, and you've been doing some of that in your labs. And the goal is really to evaluate new ideas for new memory architectures. So there are many potential evaluation methods, right? Simulation is not the only method. The question actually, the question is bigger. This is one question, of course. How do we assess how an idea will affect the target metric X? Right? There are many evaluation methods available. One is theoretical proof. You can basically set your stage and you can try to prove that a cache you add is going to improve performance by 50%. Good luck with that proof. You have to make a lot of assumptions that makes this proof unrealistic in the end, or limits the workloads to a very small set of things that are available. So this is very difficult in general in many things we do in computer architecture. Analytical modeling and estimation is actually something that we can do, and it's very useful also. So you analytically model, for example, bandwidth. If the bandwidth is this much, I'm going to get this performance. And if you can actually come up with an analytical model, linear model or some sort of model, quadratic model, that takes into account some of these metrics and basically gives you a performance. Of course, you need to feed that model with some inputs that represent the workload, for example, and maybe the machine. And this is possible to do, but it's not always easy to come up with analytical models. We're not going to talk about analytical model in this particular lecture. We're going to talk more about simulation. But this is actually within the realm of architecture, and a lot of architects can do it. And this is actually a very useful tool to do it. Even before simulation, if you can analytically model something, that could be very useful. But you may miss things with analytical model. Simulation is what we're going to talk about. This is basically simulating something that doesn't exist, for example, or that does exist so that you can actually gain some insight into it without going through all of the mess that happens in a real system, right? And this happens at varying degrees of abstraction and accuracy, as we will discuss. But then that's not where it ends. You can prototype with a real system. You may have an idea, and you actually implement it in an FPGA, for example, in a prototyping tool, or some other type of system, and you try to guess what your idea will affect in terms of performance or energy. That's also interesting. And we actually seen examples of this, like PyDRAM. I'm going to flash some things soon until we get to simulation. And eventually, maybe you actually really implement your idea completely and test the answer to that question, basically, right? You have an idea, you have a cache, you implement it, the entire system, and you get results, right? This is, of course, very tough, right? And if you have a billion ideas, which every researcher should have, not all of them may be good, of course, then you're in trouble if your goal is to implement every single one of them. This is another reason why those software people are wrong. You cannot implement everything. Okay, so basically, whenever you have a question like that, it's a scientific question in the end. You have a lot of tools that are potentially available to you, right? You may need to develop some of these, but you have these methods. The question is, which one do you use, right? So in computer architecture, usually simulation is at the center because it gives you a lot of insight if you do it right. Analytical modeling is also quite useful if you develop the model well. Theoretical proof is usually extremely hard because you cannot really model the workloads in a way easy. Real implementation is usually prototyping. You can do also with a little bit more work, but it may not reflect what you're going to eventually implement. Real implementation is usually very, very tough. Or if you do it, or there's a trade-off over here, right? You can choose to do a real implementation of an idea X, but then you may be missing out on a million ideas that you cannot explore because you don't have time to implement these, right? It's good to think about that, right? Research is about developing the best ideas. I think of it that way. It's kind of a hunt. Research is really a hunt for ideas, right? Instead of hunting for animals, which some people do, you hunt for ideas. I like ideas better because we should keep the animals untouched. But ideas, you basically want to test how many ideas you have. And if you implement every single one, you're going to be burned out very quickly anyway. Okay. So we're going to talk about simulation, but before that, you've seen actually prototyping in this course a lot. These are prototyping tools, actually, testing tools. And we have developed many of them. I'm going to skip some of these slides. We developed these to gain insight into real chips. So this is another evaluation method, basically. And it's a very powerful evaluation method, actually. From this, we develop models, analytical models, potentially. And we use those analytical models to evaluate new ideas that come up. And sometimes we get these models or data that we collect from the chips and use them in simulation so that we can simulate what are the benefits, for example, a new RowHammer protection mechanism that you develop. So you can combine these methods. That's why we actually have prototyping tools that are really important. And I'd encourage people to work more on these things because these could lead to discoveries that you can later model, that you can later simulate, etc. Okay, I'm going to skip these because you have seen examples of these in many lectures before. And yeah. And you can discover new things like this, which is fascinating, as we have discussed before. We also see an example prototyping platform where this sort of platform can be used to actually abuse memory chips, DRAM chips, to do row copy, true random number generation. And you can actually model this end-to-end and run an entire application. So this is actually a real prototyping platform where you can actually test what kind of benefits you could get by doing in-memory row copy, right? It's not exactly how it will be implemented in a real system. That's why this prototyping, right? Nobody in their right mind, in my opinion, should implement row copy by abusing timing parameters. A much better way of really designing the DRAM chip such that it's robust and you don't abuse. This is part of the, I don't want to call it standard necessarily because standards limit innovation, but this is part of the interface that you expose to the memory controller. And you actually design that. And it's very nice. Here, we make do with whatever is available to us. Right? And it's very important to do things like this also because, again, you can examine things, you can study things that are not possible with simulation potentially. Right? There's actually benefit to this prototyping tool. And you also demonstrate something that is not possible to demonstrate with simulation. Right? Again, you may have these software people who don't believe things. They basically say, oh, I don't believe that this works in DRAM. Because, you know, the Earth is flat or whatever, right? Circuit simulation is not supposed to be believed because they don't understand what's going on underneath, right? But now if they see, oh, this thing actually works in DRAM, even though they don't understand what's going on, they can empathize with it, right? So it's a good tool to convince non-believers, let's say, assuming they are to be convinced. Some non-believers never get convinced. It's good to think about that also, right? There's an audience that can be convinced, and there's an audience that can never be convinced. Forget about this part. Maybe they will eventually get there, but they're kind of there's clearly a curve, and they're kind of at the very tail of the curve, whatever curve you want to say. Okay, anyway, so that's the prototyping tool, and we've seen that also. And I think this is a very nice prototyping tool that we have developed. There needs to be more such prototyping tools, in my opinion. And maybe some people here are interested in developing those. Okay. Okay. So now let's get into simulation. Basically, it's not easy to evaluate or explore architectural ideas. There are many, many things that affect this difficulty, right? One is answer is usually workload dependent, right? Because when you design architectures, you're not designing the architecture for everything in general, unless you're designing a general purpose computer. But even general purpose computers, if you think about how they're designed, you design it for a set of workloads that you are aware of. It's very difficult to basically design something and expect that it performs very well on everything. You normally benchmark in some way, right? So, and the answer is usually workload dependent. Workloads can be very different from each other. In fact, designing a general purpose computer is much harder than designing a specialized computer because you need to cater for many workloads, right? If you look at a machine learning accelerator today, it's matrix multiplication. It's a bit boring in that sense. A lot of people are, for some reason, investing a lot of effort in it. But designing a general purpose processor is much harder, actually. Okay, it's good to keep that in mind. So yeah, there are many, many ideas that we have looked at. They're all workload dependent in the end, right? Their benefits are all workload dependent. And workloads change. You're not designing for today. Today is today. If you're designing for today, you're going to miss the boat 5 years down the road. It's always good to think about that, right? When you design something, it takes time for that to get adopted. And by that time, workloads may have evolved. Right? For example, there are a lot of companies who have designed machine learning accelerators for CNNs. They specialize on CNN, convolutional neural networks. That was the hot thing a few years ago. What is the hot thing today? What? Transformers, exactly, yes. Most people would not call them transformers, sorry. You're still very technical, you know? Most people would call ChatGPT or LLM, right? Yeah, exactly. And today there are, again, these flock of people who are designing things for LLMs, right? It's going to change in 3 years, right? And you'll have 10,000 papers that are useless. I mean, almost useless. Epsilon. I'm not saying all of them are useless, but it's good to think about these things in a broad perspective, right? Okay, so workloads change, basically. We've kind of seen that proof. And if not, I'm happy to connect you with people who were actually designing these CNNs and they got burned. Or machines for CNNs. And also, systems are complex, basically. There are many design choices and parameters. Even in an accelerator that's very specialized, you still need to make a lot of design choices, like buffer sizes, how many functional units, what kind of functional units. So these actually explode very quickly, right? If you had to implement every single one of them and figure out what you had to build based on real implementation, you will never implement anything. I mean, you will never get to the best implementation that you want to find. So in the end, architect needs to design or decide many ideas and many parameters for a design. So it's not easy to evaluate all possible combinations. That's where analytical modeling actually can help, if you can do analytical modeling. And also simulation could help if you can efficiently explore the design space by simulating hopefully a fraction of the combinations, right? And on top of the system parameters may change as well, right? A parameter that may be useful for workload X today may not be useful for workload Y 3 years down the road, because the workload Y may demand a lot more memory, for example, right? That's just one example. So basically, it's not easy to evaluate things. There's no easy answer to these things also, right? But these are all good things to think about. I believe simulation actually makes a lot of these easier. In the end, you design a simulator that that's capable of simulating what you may want to build at some point, and you make it flexible enough such that you explore a lot of, let's say, dreams, a lot of ideas, right? That's why I call this the field of dreams in the end, right? It's kind of like similar to dreaming, actually. An architect, in the end, is a dreamer. They're a creator, right? They create things. And simulation is really a key tool of the architect. It's essentially testing which dream is better, right? It allows the evaluation and understanding of non-existent systems that you dream about. Like processing in memory, for example. And you can simulate them. It enables the exploration of many of these dreams, hopefully efficiently. We're going to talk about efficiency of simulation. Because you don't need to build every idea that you have, right? You just simulate. And as long as your simulation is accurate enough, I'm not saying perfectly accurate enough, you can decide which dream is better, right? Or which dream you want to pursue in actual reality. It can also provide you a reality check of the dreams. You may dream something, like some idea, like branch delay slot, for example. How many people know about branch delay slots here? Okay, you have taken my course or some course. How many people do not know about branch delay slots? Just okay. You should look at DDCA. But the branch delay slot, the basic idea is in the original MIPS architecture, MIPS designers decided that after every branch, you should have an instruction slot. The instruction that comes sequentially after the branch should always be executed. Why did they do that? Because they designed this for a two-stage pipeline. In the ISA, they thought, oh, everybody's going to build two-stage processors, meaning if I actually ensure that the next instruction is always executed, I don't need to predict which way this branch will go. It's the compiler's job to put some independent instruction after the branch so that that always gets executed. Right? That's an idea. That's a dream. Right? Now, if you had a good simulator that simulates five-stage pipeline, maybe they would have figured out that this is a bad idea. But they thought only two-stage. So there are multiple issues actually with this idea, but a simulator could have caught some of the issues by changing the parameters. Right? One of the issues with that idea, one of the fundamental principal issues is it's tying the semantics of an instruction to a particular microarchitecture someone has in mind, right? And that's the big issue actually. You should try to avoid that as much as possible, especially in general purpose design. Right? If you're doing general purpose design, don't tie the semantics of your instructions to particular microarchitectural choices that you're making today, because 5 years down the road, those choices may be terrible. And they figured out that it was terrible. So you don't see branch delay slots in many ISAs. Spark also has it, by the way. Anyway, they also had a load delay slot, which is an even worse idea. Okay, anyway, basically, a simulation enables you to check the reality of your dreams. And also, it can help you decide which dream is better. But simulation also enables you to fool yourself with false dreams, especially if you don't design your simulator well, such that it can provide an accurate or accurate enough evaluation of which idea would be better, assuming you implemented it. Or you may misuse the simulator, like a lot of people are doing these days. That's possible. We're going to get to that also. Basically, you need to be careful. I mean, this is true for everything that you do in science in the end, right? Or development or engineering. You got to be careful, right? You got to know what you're doing. But in this case, you got to be extra careful because you're designing the simulator. And you need to make sure that you're designing something that actually accurately reflects, or accurately enough reflects how an idea would perform. And this, in part, is experience, right? This is not because you don't have a reference model for what is going to be built in the future, right? This is your reference model. Simulation is your reference model. And if you get it wrong, such that it doesn't have a accurate enough predictive power of what some metric, how some metric will change with some idea, then you make the wrong decision potentially, right? And this is, again, always an architect's problem, right? An architect, for example, who designs a building, similarly, they design a building and they make some choices, and the building may be terrible to use for education purposes, for example. It may be great to use for storing goods. It may not be a great place for educating people, right? Or having lectures. Right? Think about that, right? It's very similar, basically. By the way, architects also use a lot of simulation. They're one of the first professions who have adopted heavy simulation using computer-aided design tools, if you think about that. And a lot of architecture today is done using computer-aided design tools. Although those drawings, I guess people still need to draw, but they're getting replaced with computers. Okay. So we're talking about computer architecture. It's very similar to real architecture. Okay, let's talk about why we want to have high-level simulation. So once you decide you want to do a simulation, then the question is, at what level of fidelity or at what level of abstraction do you want to do simulation? We're going to talk a lot about high-level simulation, which you're also doing in your labs, actually. The problem is if you want to model things at a very low level, let's say transistor level, or RTL level, which is gate level, right? It's very slow, basically. The design space, especially for design space exploration, but even for a single design space, for if you want to run a workload long enough to get some metric, power, performance, etc., it's too slow, basically. It's too time consuming to design the simulator first, and also evaluate. Hopefully that makes sense, right? So what we do is we raise the level of abstraction, especially if you want to predict the performance of a good chunk of a workload in a particular design, basically. Even with a single workload, you run into problems, basically. You may spend days and days and days in architecture, in gate-level simulation. And if you do circuit-level simulation of every single, let's say, transistor that is there, first you need to design all of them, which is very close to designing real hardware, by the way. But then simulating them actually takes a long time. Okay, basically it's not tractable. There are many design choices that you want to explore, and it becomes actually crazy in the end. So our goal is really something else. Explore design choices quickly to see their impact on the workloads that we're designing the platform for. I mean, of course, at some point you'd go into RTL simulation so that when you're closer to implementation, for example, because you need to actually implement something. And you normally don't go from high-level simulation to implementation. You have multiple steps over there. You simulate, meaning you put things into RTL, implement it at that level, and then simulate it to see if your expectations are reasonable, let's say, but you don't do design space exploration at that level in the end. Okay, so this brings me to different goals in simulation. Basically, if your goal is to explore design space quickly and see what you want to potentially implement in the next generation platform, high-level simulation is actually a very good choice. Or what you want to propose as the next big idea to advance the state of the art, which is really research, right? What we do. The goal here is to mainly to see the relative effects of design decisions. You don't care whether design decision X versus Y you don't care whether the result is exactly accurate, basically. You care, oh, is my decision X 10x better than design decision Y? Right? 10x. That depends on the fidelity of the simulator, of course, but maybe you're fine with 5x as long as the error that you have is not that large, or 5%. I was going to say 5%. If your fidelity of your simulator is good enough, 5% may be an okay difference between an idea X or idea Y, right? In terms of performance, let's say. But you normally evaluate many metrics when you simulate. But the goal here is very different from accurately modeling a system, basically, completely accurate. Accurate enough is the key here. Or, this is a very different goal. I'm going to give you some goals over here, maybe not all of the goals. This is another goal. You want to actually simulate an existing system that already exists, this thing, for example, and you want to match the behavior exactly so that you can do something with it. For example, debugging and verification at cycle level accuracy. Right? This is what a lot of companies do after they design or while they design a processor. And they want to actually understand what's going on. For example, if there's a performance bug or even a functional bug in an actual processor, which may be very difficult to figure out in that processor, they go to the simulator and they try to replicate that bug. And once you can replicate the bug in your simulator, then you can fix it a lot more easily because you exactly know what's going on in your simulator, whereas you may not know exactly what's going on in the system because there's always a gap between simulator and real implementation also. Okay, so this is actually a very important goal also. Or you may want to propose small tweaks to the design such that you improve the performance and energy. Right? So I've designed this processor that's running over here. I have a very accurate simulator that matches its behavior with maybe 0.5% accuracy difference. And I can propose small tweaks to improve its energy. Right? Real companies actually do that. They're really smart people who are very meticulous. Their job is to actually make sure that simulator doesn't deviate from the performance of the real system. I met a lot of people who have done that job, and I actually respect them a lot because they are actually very, very detail-oriented and meticulous, and they're actually very good at finding those bugs. So in this case, you'd still do simulation, but the goal is very different. You really want high accuracy over here. You really want to find that bug that affects your real design so that you can fix the real design with the mechanisms that you added to the design. Maybe you can bypass some logic, right, after you find things by matching the behavior of an existing system. So you can see these are very complete different goals. I don't want this simulator if my goal is to do research, because this runs like a dog. It's not a fast dog. Okay, there are other goals in between also. There could be many other goals, clearly. For example, you may want to refine the explored design space without going into full detailed cycle accurate design. So there may be something in between, right? Or you may want to gain confidence in your design decisions made by higher level design space exploration. So you go to the next level of simulation, potentially. So that will bring me to simulation as a progressive refinement soon. But before I go into that, let's talk about 3 metrics to evaluate a simulator. I kind of talked about accuracy a lot, but I also mentioned like how long it takes to design a simulator. So there's 3 metrics actually 3 plus more. Speed. That's how fast does your simulator model whatever you want to model. A workload executing on a processor, for example. Flexibility. How easily you can change the simulator such that you can model whatever you want to model next. And accuracy, basically, what is the error of the simulator compared to what you're really trying to model? And this may be difficult to evaluate if what you're trying to model doesn't exist, right? And that's the architect's dilemma, as we discussed, right? So speed, I think we already discussed how fast simulator runs. There are multiple metrics. How many instructions per second you can simulate, for example, how many cycles per second. What is the slowdown compared to a real system, if you can evaluate that? Flexibility is how quickly one can modify the simulator. We already discussed that actually. And accuracy, again, I think I already discussed that. This is also called simulation error. And the relative importance of these metrics varies depending on where you are in the design process and what your goal is, basically. And we already discussed that also. And you can trade off between these. Speed and flexibility affects how quickly you can make design trade-offs decisions. Let's say time to market or time to an idea. How fast you can evaluate an idea and make an impact, right? If you have a great idea and if you work on the simulation for 3 years, maybe somebody actually already publishes that idea or patents that idea and you're dead. Well, not dead, but your idea is dead from your perspective, let's say. Okay, accuracy affects how good your design trade-offs or decisions might end up being and how fast you can build your simulator also. So there's another metric over here that I didn't mention, simulator design time, right? That's actually also important. This is different from the speed of simulation. It's really it's related to actually flexibility of simulation, but it could be, a simulator can be very flexible, but the design time may be very long to begin with, potentially. Flexibility also affects how much human effort you need to spend modifying the simulator. These are actually really, really important. These can make or break your company, if that's your goal, or these can make or break your research idea as well. And I've seen both of them happen. So you can trade off between the 3 to achieve design exploration, design space exploration, and decision goals, clearly. Normally, you get at most 2 out of the 3. Konstantinos may argue against this, but I will argue that he will be wrong. You basically get speed and flexibility maybe, but then accuracy you need to give up. Or you may get high accuracy, and then you give up speed, usually. These usually go against each other. But you try to get all of them as much as possible. Maybe Konstantinos will convince you later with Virtuoso, he gets most of it. Not today, though, and he talks about virtual memory. Is that good? Okay. Okay, high-level simulation. Today, I don't have Ismail, so I have the Greek counterpart, you know. You got to balance the Turks and Greeks. He's upset that he came to the lecture now. No, he's okay. Okay, so basically, high-level simulation is the idea is to raise the abstraction level of modeling so that you give up some accuracy. Basically, you explicitly give up accuracy. That's the core of this idea, basically. Because if you don't give up accuracy, you're not going to get speed and flexibility. And that's true in Virtuoso, Konstantinos' baby. That's true in many other simulators also. Compared to something that's really accurate, you're going to be inaccurate. No question about that. But you'll gain something which is speed and flexibility. And hopefully, quick simulator design, right? That's the beauty of high-level simulation. And clearly, with every idea, it also has advantages and disadvantages. The advantage is you can still make the right trade-offs and can do it quickly, right? Assuming you're doing some things correctly, of course, right? All you need to do is to model the key high-level factors that you care about, and you can omit corner case conditions. Or you can omit things that you don't care about, right? That you don't want to modify. And that's one of the things that Virtuoso has. This is, again, Konstantinos' baby simulator. I think that people are using it, right? Yeah, okay, that's good. For a lab, oh, okay, really? Is it already out? Okay, yeah, good news. You're going to use Virtuoso. So you can talk. You know who Konstantinos is over there. If there are bugs, go and bug him. Every simulator has bugs. Every piece of software has bugs. There's no non-buggy piece of software, despite what software people may tell you. Although there are some languages that make it easier to actually spot or find those bugs, but most languages are not. Most languages that are used in the field are not those languages. Okay, anyway, all you need to is to get the relative transaccurately, not exact performance numbers. That's our goal in high-level simulation. Again, this is a very conscious choice that we make, right? Otherwise, we cannot really make decisions quickly among many ideas. But the disadvantage, of course, now this high-level simulation, the fact that consciously we're trading off accuracy for something else opens up the possibility of potentially wrong decisions. And you need to be very careful about that. In my opinion, there's no other way around this. You have to minimize the risk somehow. And here, experience matters a lot, or some ways of testing matters a lot. Testing, validation, verification, as much as possible. But experience is also very important. Okay, how do you ensure you get the relative transaccuracy, basically? If you forget something that's really important to model for what you're trying to examine, for example, you may not get the relative transaccuracy. That's the key, basically. If something happens once in a blue moon, and you decide not to model it, for example, some interrupt that you don't care about much, that's fine, perhaps. Right? But how do you actually reduce the possibility of potentially wrong decisions? I think one way of doing it in simulator design is really keeping track of what happens. For example, something you don't model. You know you don't model. You made the conscious choice not to model. But you count how many times you actually see it. Right? And you say, I don't model it. And if that count is actually substantial, maybe you go back and say, oh, I'm going to model it now. Right? Maybe for this workload. So this is one way of consciously trying to avoid potentially wrong decisions. Right? But for this, you need to be aware of what you're not modeling. And how are you aware of what you're not modeling? You need to know what you are modeling and what you're not modeling really well for a future system. So you need to know what you're doing, basically. You cannot treat a simulator as a black box. This is true regardless of whether or not you develop the simulator or somebody else developed the simulator and you're using that simulator. It's critical to know what you're doing. Hopefully that makes sense, right? Because we have papers published where people don't know what they're doing and they write things about simulators. Lisa is going to get to that. So don't assume that all papers that are published are good. Okay. But there are ways to actually try to avoid the wrong decisions, essentially. So some of this actually comes with experience also, no question about that. If you have written a lot of simulators, if you actually are careful about software engineering, if you actually always question, okay, am I modeling X, Y, Z, T, then you can actually avoid some of these wrong decisions. But again, in the end, it may not be possible to avoid some of them. Okay, simulation is also a progressive refinement. I kind of alluded to it earlier, but you start with some high-level modeling. It could be very abstract. It could be written in a high-level language. I like C, but I guess these days the C is not that popular. What do people learn these days as the first language? C++, really? Okay, what else? Java? What else? Rust? No Rust, okay. I think Rust would be better actually, but maybe. Python? Okay, that's terrible. Okay, you can do it. You can have ChatGPT write the simulator and see how good it is. That's your challenge. Okay, you start with high-level models, and then you refine it to get medium-level models, less abstract. And then at some point, you make some design decisions based on those models that you develop, and you actually design something very low-level, like RTL, register transfer language model, gate-level model, with hopefully everything that you care about modeled, and simulate that and look at, for example, critical path. So at the high level, you don't care about critical path, perhaps. You have other design decisions to think about, right? But as you refine, there are some other design decisions that may come in, like critical path of a circuit, right? And that's a lot easier to look at in the low-level models clearly. And then you go into real design. And then once you have the real design, actually, you can update your models, right? Because now you have hopefully some real design, some reference, at least a portion, a reference that can validate a portion of the high-level model and the medium-level model and the RTL level model. But these are actually simulations. RTL, never confuse RTL with real hardware, because RTL is not real hardware. How many people think RTL is real hardware? I should have asked the question earlier. Sorry. Yeah, but RTL is not real hardware. RTL is actually a model, again. It's a very low-level model, but it's a model. There are lower-level models than RTL, which is transistor models, for example, right? And you actually put together all of those models, spice models, for example, circuit models. There are even lower-level models than that model electron flows, et cetera, like TCAD models. So that all of those are models. Only real design is not a model. Although that could be a model, according to some thinkers. But anyway, let's keep it as a not model for now, because that's something we can touch maybe. But basically, real design is something that you can go back and fix the earlier model. So RTL is a model. For example, in RTL, you do something. Usually, RTL has some sort of error compared to real design. And that's usually within like 1 to 2%. And companies try to keep it within 1 to 2% as much as possible. If it goes to 3%, then that person that I talked about who actually wants to keep things accurate, they have their nights cut out for. They're gonna go and figure out why it's 3% and why isn't it 1%, right? So the reason it's a model is because once you implement, there are things that do not necessarily reflect RTL, right? Because somebody actually implements these things at the very low level. You may actually have some bugs, for example. You may actually have things that are not, the critical path may not work well because you're modeling the critical path. And as a result, your critical path may be different. So your performance may be different. And who guarantees that the RTL is going to be exactly implemented, right? Because somebody designed the RTL and then somebody does a custom design in some part of the processor. And now that RTL is immediately out of date because they don't follow the RTL. That part of the design is custom, right? And they decide, oh, at that point in time, I can design this much better than what this RTL designer did. So I'm going to fix that, but I'm not going to tell them. And the RTL doesn't get updated, basically, okay? So it's good to think about these. So as you refine, meaning you go down the above list, abstraction level clearly reduces. Accuracy hopefully increases, but not necessarily, actually. If you're not careful, a high-level model may be more accurate than a medium-level model, for example, because, again, it's a trade-off, what you're modeling and what you're not modeling. Flexibility also reduces. Speed likely reduces again until you get the real design. In the real design, you're running things, but you're not simulating anymore, right? Okay, and you can loop back and fix the higher-level models, as we discussed. So it's good to have actually all of this as an architect. If you're really good at everything, that's really great. And if you're at a company that has been designing processors for many years or hardware for many years, they actually have a lot of these models. And they actually go through this flow every time they design a new system, new processors, for example. And over time, they can accumulate a lot of real designs and they can fix the accuracy of the higher levels. But over time also, unfortunately, what happens in software is complexity increases. So at some point, somebody in the company says, if they're smart, we're going to scratch the older model and rewrite it because this simulator has become a mess. No pun intended here. Okay, so making the best of architecture is what I just said. You become comfortable at all levels of refinement, including the extremes. And a good architect really knows when to use what type of simulation, and more generally, what type of evaluation method. Again, part of this comes with experience also. And a part of the experience you're gaining in this course, for example, by using different types of simulators. And we already discussed a variety of evaluation methods are available. If you can do a theoretical proof, and for a very small fraction of problems, maybe, then do a theoretical proof. Not easy, though. For example, a lot of the caching theory was developed assuming access patterns that are friendly to least recently used type of accesses. And they basically, this is called the cyclic reference model, for example. There are papers from 1960s, 1950s that talk about the cyclic reference model, and you design your cache based on that model. It works for workloads where that model works, meaning that model matches the behavior of the workload. Then you can theoretically potentially prove things, again, assuming some sort of hardware design. But again, is that general? No. And that's the difficulty of proof in general and theory. Okay. So I'll go through some general issues in architectural simulation. Feel free to ask questions, by the way. I'm not going to cover everything because we don't really have time. But goal of simulation dictates many things in the end. It drives many design choices on what simulator to build and use. And remember, it also dictates what kind of speed, flexibility, and accuracy you get. And we talked about many possible goals. This is another way of thinking about it. But I'm not going to talk about this now. So what do you simulate matters. Do you simulate components or a full system? Do you simulate programs or traces of a program? How do you simulate it matters. I'm not going to go through all of these, but there are many choices when you design a simulator. I'll show you one example later on. Where do you simulate matters. And where do you simulate each thing you want to simulate? Do you actually do it in software? Or do you actually accelerate with hardware, with FPGAs, for example? Right? Your simulation can be accelerated also. Right? A lot of people actually looked at accelerating simulations so that you can actually run much more complex software, because software, doing simulation purely in software is slow. And when do you do things in simulation, basically? This goes into the guts of the simulator design. But for example, if you're executing a program, when do you execute things in simulation? Do you actually execute something and you know all of the information about what is supposed to happen for an instruction before you actually simulate the timing for that instruction? There are potential uses for that. You can do perfect studies, for example. If I actually can predict the direction of this branch perfectly, then I can actually look at the benefits that I get in terms of performance if I have this sort of a machine, right? If you have the information about the branch right away before you actually feed it to a timing model and that models a pipeline, then you can actually do things like that. So there's actually a lot of benefit to having information about an instruction whose timing you're going to model early on. But there's always a downside. This also opens up some potential for bugs, because you may actually use some information that you may not actually have available if you're actually correctly simulating the timing. So you need to be very careful what you're doing in the end. And some of these become more understandable if you actually deal with simulation. Right, Rahul? Okay, he agrees. Okay, so there's inputs and outputs. Again, I'll go through these relatively quickly, but because you're going to see a lot of this in your labs. You've already seen actually some of these, but you're going to see more. Thanks to Konstantinos. Is the Virtuoso lab up yet? When is it going to be up? Okay. Now 5 or 6 or 7. Okay. An optional lab, 5, 6, or 7, I guess. Yeah. Okay. 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 But if you want to learn about virtual memory, that would be good, right? Yeah. Okay. Inputs can be program binaries or multiple program binaries. It could be system or state checkpoints. It could be traces, as we discussed earlier. Outputs can be program results, functional. There are functional outputs and statistics about functional execution, or there could be timing related outputs. We're talking about performance, execution timing of each program. How long would it take on this architecture that we're modeling? System throughput of all programs. There are many metrics over here that you've been seeing in papers that you've been reading, for example. And there could be statistics about timing and performance events, and also energy, and also other potential metrics, right? So you can collect a lot of metrics related to timing, functional, energy, etc. There are many issues in architectural simulation, which I am not going to get into, but functional versus timing, for example. When do you do the functional simulation about an instruction? Functional simulation is basically the semantics of the instruction, for example, right? When do you get that information? Timing is basically, you model the timing in the microarchitecture that you're executing the instruction. And these are two distinct things, but they do affect each other, clearly. Because the functional result of an instruction, for example, may determine, or functional inputs to the instruction may actually determine the timing. Multiplying a value by, if you're having a multiply instruction, if one value is 0, that could be executed much faster. Right? It's good to think about these basically. Functional and timing affect each other. You may do a full system or component simulation. So full system, when do you actually execute full system or components? What should be modeled? Do you model the operating system, virtual machines, memory allocator? Do you model everything when you do full system simulation? I think Konstantinos will talk about that when he talks about virtual memory, so I'm going to leave it to him. Do you simulate the complete workload, or do you simulate a part of it? Right? How do you form the workloads to simulate? What parts do you simulate? This is actually an important question because modern workloads are huge. Right? If you simulate the entire workload, you may be simulating for days, especially if you have a slow simulator. So normally what people do is they try to sample the important parts, and there are multiple methods for sampling. Again, I'm not going to go into it. There's a lot of statistical theory that can help how to sample. But there's also other methods for sampling the hot parts of a program, for example. There's no perfect way in the end. You need to simulate something, right? Now, this becomes easier if your programs are actually formed of kernels that are repetitive, right? Machine learning kind of comes to mind in this case, but if you're modeling just matrix vector multiplication, it may be easier, right? But if you're modeling something much more complicated, a much bigger system that consists of many different types of parts of kernels, then it becomes harder to decide what to actually simulate, right? And warm-up is also an important issue, right? Sometimes this used to be actually a bigger issue, but it's still an issue, actually, I would say. If you don't warm up your simulator, you may actually be getting results from the beginning of a program, right? Or the microarchitecture is still not warm, and you've started executing, and you get a lot of cache misses, for example. When you warm things up, maybe you don't get a lot of cache misses, right? So you basically need to think about that. So all of these tables, may need to be warmed up. Yeah, this is a very old simulator. How many people know about simple scalar? Okay, how many people use simple scalar? Okay, good. You used it? Okay, hopefully you don't have it in Virtuoso. Good. I was talking to some professor recently, and they said they're still using simple scalar, and I said, why? This is actually one of the earliest open source simulators in computer architecture. It did a lot of good, in my opinion, because it enabled people to simulate. It did a lot of bad because a lot of people abused the simulator, meaning they use it for things that it doesn't model very well. But you can see that even with simple scalar, there are different models, right? SimFast is, I think there's no timing. You can see that it's only 400 lines or so. And this is a very old slide, by the way, from Todd Austin, I think, yes, who was a co-author of the simulator. And basically, this is a functional simulator. There's more functional simulator that has some checks. There's some profiling with stats. More functional simulator that actually has cache. I wouldn't call it just functional, but cache statistics. But I guess it's functional cache statistics, not timing. And then there's a timing simulator that's out of order execution. This is a very processor-centric simulator. Memory doesn't exist, except for modeling of latency of memory as, so there's a cycle count in the simulator, and you increment the cycle count by a parameter, a fixed parameter called memory latency. Cycles plus equals memory latency. It's good to think about that, right? We're talking about, of course, 1990s. But this also shows how processor-centric we are in our thinking. It's a good simulator. Well, if you're careful about what you're doing, it's a good simulator for doing processor-centric studies, but terrible for memory studies. And a lot of people did memory studies with it and worsened this memory issue in the sense that there's a lot of crap, in my opinion, as based on that cycles plus equals memory latency. So what do you fault this to? Do you fault this to simulator writer? Or do you fault this to simulator user? I would fault the latter. Because if you're using the simulator to model DRAM, and what you're doing is that, or some prefetcher maybe you should build a better model, right? Clearly, a simulator writer is not going to build the model that you want, or that everybody wants in the world. you as the researcher are responsible for building a model that fits your purposes. Right? You cannot abuse a simulator. Does that make sense? Do you agree, Rahul? Okay. So every simulator has its upsides and downsides in the end. Has basically a set of things it models and a set of things it doesn't model. If you're going to develop an idea and evaluate it on things that the simulator doesn't model, you'd better know exactly how that simulator works and essentially expand that part of the simulator, assuming that's the simulator of choice that you're going to use. Right? And even then, even in parts where it is modeling, you have to check, is this modeling the thing that I want to model? Is it modeling it accurately? So it's good. It's very important to understand your simulator. Okay. So this is another simulation paper. If you're interested, you can take a look at it, but I'm not going to talk about this. There are simulator papers that talk about things. This is another simulator that's actually accelerated using an FPGA. It's a paper by Derek Chu and Cal in 2009. And basically, you have some functional model that executes and communicates some traces to an FPGA. FPGA models the timing and returns some information such that the functional model can proceed. Functional model essentially executes the program and gets the functional results, and the timing model is mostly done on the FPGA. Right? Why does the functional model and FPGA timing model need to communicate? Because timing model, for example, when a branch misprediction happens, timing model knows exactly when that branch misprediction gets resolved. And it communicates that information to the functional model such that the functional model can change the instructions at that point in time, right? Okay, so this is also very interesting. People have tried to develop accelerated simulators using FPGAs. Okay, there are more issues, clearly. Validation of accuracy. How do you validate? Functional accuracy is easier to validate, but timing accuracy is much harder, especially on a system that nobody has ever designed. Right? How do you validate? Do you do it offline? Do you do it online? It's always good to have online checks in your simulator, sanity checks, basically. If something is wrong, then the simulator should provide a warning or an error, right? And again, this is actually general software design, I would say. Okay. But if you leave it to ChatGPT, I don't know what happens. Good luck. I think I'm not going to fly if people start designing things with ChatGPT, designing planes. I'd rather walk. Okay. Simulation acceleration, we talked about that. Better software engineering actually goes a long way, but it's not enough, especially for large workloads. So hardware supports can be important. Trace-driven versus execution-driven, it's also important, but I'm not going to. So for example, one thing that's important is whether you model the wrong path, right? So you make a branch prediction. Branch is mispredicted. What do you model? Do you insert wrong path instructions into the pipeline and model if their effects on performance? Or do you just stop fetching? Right? Clearly, stopping fetching is not realistic, right? But maybe it's okay. It's good to think about that. Depends on what you're evaluating. So we did a lot of work in this area and showed that wrong path modeling is actually useful. And wrong path can be useful for performance also. Okay. Okay, I'm going to skip these. There are many issues. Okay, there are many simulators, like Ramulator, that you've been using. How many people have used Ramulator so far? Not yet? Okay, that's good. How about Ramulator 2? Okay, some people. Okay, don't we have a lab that's Ramulator? Yeah. Okay, lab 4, right? Yeah, okay. Okay, labs are all reordered maybe. Okay. Okay, in one of the labs, you're going to use Ramulator 2. I'll go through this relatively quickly because I want Nisa to cover some of these, but this is a simulator that we developed for a long time. Experience helps, I will say that, but I have started actually developing the simulator when I was at Microsoft Research, our earlier papers. It was a crude simulator, and we actually developed it in our group at CMU for some time, and eventually we decided to release it to the world, and it's actually been used by industry and academia very heavily. Also, industry folks use it at major companies, and they give us feedback on the simulator. We fix some bugs. Some not so nice folks actually use it, abuse it, and write papers saying that this is bad. But I'll let Nisa to talk about that. that goes against all of the open source principles and also maybe scientific principles, as we will discuss later on. But basically, this is a simulator that's actually, we believe that it filled a gap because DRAM and memory controllers that you very well know of in these lectures have been changing a lot, and there are many new ideas that are coming and many new controller designs. And we want an easy to extend and fast simulator. And you can see some of the DRAM landscape from the Ramulator paper in 2015, right? So we designed a simulator that can model many DRAM standards, and also new things. And at the time, it was faster than any other open source simulator that modeled memory, and it's modular and extensible. So that you can do many studies that you have seen in this course. This was from the original Ramulator paper, where you can actually look at, for example, different DRAM types and how they affect performance. And this study is not possible in a real system. When we submitted a paper like this, not the Ramulator paper, but the later paper that I will talk about, we wanted to understand the interaction of the workloads with DRAM types. And one of the comments we got, along with a nice rejection, was, actually, maybe that was this guy, I don't remember. I think it was published in Sigmetrics in the end. Fine, I shouldn't pick on Sigmetrics today. But it was this guy. Basically, one of the comments we got from these brilliant reviewers was, oh, you did a very nice study in simulation, but you should do it in real hardware. Reject. Okay, basically, these folks wanted us to study the effect of all of these memories on real hardware, and there's no way you can do that. Because there's no real hardware that exists that keeps the processor constant and changes the memory interface, because no one in their right mind is going to put 10 different memory interfaces in a single chip, or design a single chip with 10 different memory interfaces or 10 different versions with different memory interfaces, basically. So you can see that sometimes reviewers don't think, or they're malicious. I don't know what that is, but it's good to think about this also, right? So if you're a reviewer, never make comments like this before thinking. Can this be doable? If I had to do this thing, am I really able to do it? That's a very basic question to ask. That's like validating your simulator, right? Validating your thinking. And if the answer is no, this is not doable, then don't write that comment in the review. It's good to think about this, you know. When you're also reviewing papers, though, don't write that comment in your reviews. Okay, so that's the Ramulator paper. You're going to look at it. And this is open source. It's integrated with other simulators like Gem5. It's reproducible. And we actually had a project course at some point. It's not running right now, but you can find a lot of information about Ramulator. Now we have Ramulator 2.0 that Nisa is going to describe in more detail. But this is my bonus assignment for you. Maybe you already read these papers, but yeah, review them. There are many example studies using Ramulator. I'm not going to go through all of them, but this was one of them that I mentioned earlier. This appeared at Sigmetrics, but was rejected from ISCA for the reasons that I said. But you can actually study essentially what effect a type of DRAM will have on a particular application. And I can try to understand why that effect exists, right? It's actually very useful to decide what kind of DRAM to use. And we've seen these slides actually in an earlier memory latency lecture that Mohammed delivered, right? So I'm not going to talk about these in detail. You can come up with a lot of basically insights that may not be reasonable. For example, in this work, we found out that for some class of applications, low power memory can provide energy savings without sacrificing significant performance. So that's actually a useful insight to think about. Okay, I'm going to skip these. So there's more papers, RowHammer, which we studied based on Ramulator. And we actually released a lot of RowHammer studies or RowHammer protection mechanisms with RowHammer. And more recently, we've covered the Kronos paper. That was also based on Ramulator 2.0. Okay, there are other studies. A lot of Girai's PhD thesis, the simulation parts were based on Ramulator, for example. Okay, a lot of the papers on redistribution stations are based on Ramulator, actually. Okay, open sourcing helps. There's Ramulator for processing in memory, and also other models. This actually, we actually use Ramulator for processing in memory, but we also looked at some machine learning based models to predict performance over here. So that's an analytical model, I would say, that's driven by machine learning. So this paper is interesting to read if you're interested in looking at a comparison of simulation versus analytical modeling for processing in memory. And you can find more in the Ramulator course. There are a bunch of other useful simulators. Clearly, Ramulator is not the only one, but Gem5 is there for full system simulation. We've looked at MQSim when Mohammed talked about SSDs. There's hard disk simulators. The MoveSim is our processing using near memory simulation. There's Virtuoso that I'm not sure if I'll cover, but at some point you will cover, right? There's Sniper for fast processor simulation. I guess there's also ChampSim somewhere. Yeah, there's a lot of simulator basically. So whenever you're dealing with simulators, it's important for you to know what you're doing. That's really important. Or developing your own simulator for your purpose is good. But I'd recommend studying some other simulators before you do that. Okay, that's the move. I'm going to skip some of these because this is for just reference benefits. If you're interested in using some simulator, for example, we covered the move in the PIM course. I don't know if this is the last incarnation. I don't think it is. This is another simulator that's used by academia and industry that we released for SSD simulation, which we covered recently. And there's a solid state drives course that you can look at. And we actually keep releasing a lot of simulators in our website. The good news is a lot of people go to this website to actually try out some of these, which is good. Okay, Virtuoso. Maybe I'll cover it very quickly because I want to give some time to Nisa to talk about some of the things. But this is a recent simulator that Konstantinos and friends developed. And the goal is really to evaluate some of the most difficult things to evaluate, which is when you actually modify both the hardware and the operating system. How do you evaluate things accurately and also flexibly? You may have many ideas, like Konstantinos does, and you want to test these ideas. How do you test them quickly, right? And also accurately. And virtual memory is the domain where this is actually useful. But it could be extended for other things in operating system hardware interaction, right? So that's the idea, basically. If we would like to efficiently evaluate these virtual memory techniques that are hardware, software co-designed to make progress in the domain fast. And virtual memory touches a lot of things: software level memory management, hardware memory management unit, and system components. So you need to model these things. And sometimes these interact with each other. If you don't model them accurately, your performance results may not be good. For example, TLB performance heavily depends on the memory allocator. And that also in turn heavily depends on whether the architecture provides support for different sizes of pages and what kind of size of pages it provides support for. So you can see that you need to model multiple things. It's not just the processor over here, it's also the system. So basically you need to model, I already said this, it's crucial for new techniques. So how do you actually evaluate these in existing simulators? This also gives a nice overview of existing simulators, I would say. There are a bunch of emulation-based simulators. There's also full system simulators. Full system simulator is supposed to model everything in a system. Emulation-based, they do whatever we do. They actually, whatever we discussed earlier. They don't model some things in a system such that they achieve high simulation speed, but their goal is to model the microarchitecture timing such that they can actually get results quickly. These usually don't support OS primitives, and normally they don't even have support for these. You just need to extend them so that you estimate some system overheads. But this is kind of a hacky way of doing that, right? So these are some examples. There's also full system simulators like this. Do people use PTL sim these days? Okay. You paid that tribute. Yeah, that's a good tribute to pay. I know that guy, Matt Yorst. He was a very smart person who developed it. Yeah. I think it's actually not maybe nicer than some of the other simulators here. Okay, but basically these are full system simulators. Their goal is to actually simulate the entire OS as well as the hardware. They're full system in the sense that they can execute a full system, right? This doesn't mean they're completely accurate. They actually are sometimes not so accurate. For example, they may not model all of the hardware things inside, right? Microarchitecture. In fact, Gen5 actually has a lot of inaccuracies, in my opinion, in hardware modeling. They may be able to run a full operating system, full workload on the simulator, but the hardware timing may not be correct. So these usually have low simulation speed and they're hard to develop. So the goal with Virtuoso was to actually achieve as much as possible the accuracy of full system simulation in modeling full system, while achieving as close to possible the simulation speed of emulation-based simulators. And that's the Basically, it's that's the goal, right? You want to model both hardware and software components. And the key idea is really to model the operating system as a lightweight kernel, as opposed to simulating the entire operating system. And he's going to talk about that later, so I'm not going to talk about that. But this is kind of the penguin that tries to imitate the operating system. And it's called the lightweight user space kernel. How do you come up with these terms? Okay, it's good. I'm just joking with it. Okay, and this way, actually, you can choose modules that you want to model. Instead of modeling everything in an operating system, which is a lot of stuff, you can basically, if you're targeting, for example, some things related to large pages, virtual memory handling, and swapping, then you model only those. The key, of course, is once you model only those and not model something else, you may lose some accuracy, and you will lose some accuracy. But maybe that accuracy loss is tolerable for what you're trying to examine, because what you're gaining is flexibility and speed. Right? Remember that accuracy, flexibility, and speed. You always trade off accuracy to get more flexibility and speed. So he agrees with me in the end because he was nodding his head. Okay. Okay, I'm going to skip this. So there's more detail in the paper. You can actually use it. Apparently, you're going to use it if you do the extra assignment. I'd recommend doing it. You'll learn a lot, I think, by this. And there's a tool set that is included with Virtuoso that covers a lot of interesting things that people can build on. So hopefully more people will use this, and there will be some baseline simulator that everybody can build on and compare different ideas with. So if the simulator is actually powerful, it can actually enable comparison across the field. Many people can use it and compare ideas. Okay. And I think Konstantinos integrated this with many different simulators, Gem 5, Ramulator, Ramulator 2.0, right? Sniper, ChampSim. So it's good to look at these, and he's going to talk more about that. Oh, okay, there's an advertisement for Lab 4 over here. So there's this data prefetching championship that we're going to organize with Rahul and Konstantinos. And if you're interested in submitting to this, you're very welcome to. It's going to be based on the same infrastructure, and you'll have a head start because we're going to cover prefetching starting today after Nisa covers Ramulator. And hopefully you'll also actually have some experience with Virtuoso and the infrastructure. And if you actually do a good job, maybe you'll get a free trip to I was going to say Disney, Sydney. Sydney is much better than Disney, I think. Although there may be a Disney in Sydney also, that I don't know. You'll have to figure that out on your own. But yes, I would recommend, if you're excited about architecture and if you have some ideas on how to do better prefetching, this is a true championship to get the best ideas in prefetching. And everybody is welcome to submit in the world. So if someone is watching online, they're also welcome to submit. Okay, and then there's MQSIM that was integrated with Ramulator. So there's more, but I will leave the rest for Konstantinos' lecture on virtual memory. This is the paper. Did this paper get rejected before it got accepted? One time. Okay, you're lucky. But it became much better, right? Yeah, okay. But in some cases, like when a paper gets rejected, not much changes. But in this case, you actually added a lot more in the next incarnation. But you were going to add it regardless of the reject anyway. So it was not because of the reject that he added things. Although maybe it was fueled a little bit. No, okay. Okay. Where do you guys come up with these things? Is this ChatGPT or some diffusion model that makes these things? Yeah. I'm glad I don't have exposure to these. But my slides are kind of tainted because I use their slides. But it's fine, I guess. This is the new generation. That's how I can connect with the new generation, through my students. That's the beauty of being a professor, you know. If you want to go to academia, there's some things that you gain, even though your salaries are low. Compared to what you would gain in industry, there's a lot of benefit also. Think about that. Okay, Okay, I'm gonna skip these. I think I'm going to stop here. You put it in two places. What's going on? Okay, just to make sure I cover it. How can you not cover this huge thing? Okay, so what we discussed is applicable to simulation in other domains also. And I will not talk about this, but one of my PhD students, Lucas, did his thesis on agent-based simulation. This is actually interesting. How do you model different things, different physical things, like flock of birds? And he designed a simulator called Biodynamo that's also used in scientific simulation, actually. This is purely software-based simulation. It has nothing to do with modeling architecture. But modeling is modeling in the end. You're modeling some phenomena. And this is one phenomena that you may want to model for whatever, right? So here, you consider things as agents. Agents is a bird with position and velocity. And you may model actually different kinds of behaviors, right? Birds separate from each other. Birds align with each other. And birds act cohesively. So if you want to discover things about birds, you may model these, but you may be forgetting something, right? Everything, your model is limited to what you're modeling. And then you can discover new things over here. So this sort of agent-based simulation is applied to cells, for example, in biology and epidemiology, viruses or organisms in medicine or public health, different types of things in finance, social sciences. So this is actually very powerful. You model things as agents, and you basically have behavior of the agents and interactions modeled. Okay, this is one cell sorting example. And if you're really interested, you can take a look at what he has done. Again, this is another agent, a spherical cell with some attributes. And you can have different kinds of behaviors, like substance secretion from the cell, chemotaxis from the cell, and also mechanical forces when cells interact. And this could be useful for discovering some things about cells, for example, or how a drug, for example, interacts with cells. Again, I will not go into this, but everything that we discussed is applicable to this sort of simulation also. Speed, flexibility, accuracy, ease of use, I guess, simulation development time. And this was actually quite impactful because many scientists have used it to discover new things. Okay, I'll stop here. We have also done COVID-19 simulation, but I think that's a good place to stop. Let's see. I would say let's take a break for 15 minutes. Let's be back at 14:49. And then we will cover Ramulator, and then we will start prefetching, hopefully. Oder
Da ist gar
early. I'm early. I prepared. Yes. Is it working? Okay. presented TCuARCH. Yes, the time was tight. Yes, I was planning to present 3 more papers, but it didn't happen. Yes.
We're going to have Nisa's short lecture on simulation, but especially on validation of it. Nisa has been working on Ramulator for a long time now, right? One of the major developers and major. If you have questions about Ramulator, it's only presented the RowHammer based on.
Yes.
Uses Ramulator for evaluation. I'm going to present more because we didn't have time last time.
Yes, thank you for the introduction. Again, I will be talking about simulation a bit, with more focus on Ramulator. I already introduced myself and also Onur introduced me. I'm Nisa, I'm a PhD student, and I'm doing a lot of work in computer architecture, memory system security, and this is why I was pretty much like involved with Ramulator from early on. Again, I will basically present a brief introduction of Ramulator. Some of the slides we have covered for Ramulator's first version were mentioned in the first part of the lecture, so I will go over them quickly. So Ramulator, a fast and extensible DRAM simulator, was the title of the paper that we published in Computer Architecture Letters in 2015. And basically, the motivation behind Ramulator or developing of Ramulator and Ramulator 2 is that DRAM and memory controller landscape is changing. We have many new upcoming standards. We have many new controller designs. And this was the landscape of the DRAM-based memory in 2015 in the first paper that I will discuss. So you can see a lot of different DRAM standards from DDR3, DDR4 to HBM, which basically become much bigger after the publication of this paper. We also see some academic works that we have covered so far, such as subarray level parallelism, row clone radar, and so on. So we wanted to be able to evaluate these designs, these standards in a simulator. And to do so, a fast and easy to extend simulator was very much needed. So we developed Ramulator, a fast and extensible DRAM simulator. Ramulator still has modular and extensible architecture that we can extend it with different standards. It's provided out-of-the-box support for many DRAM standards as it was published. So we had DDR3, DDR4, all the way down to HBM, and we then also extended the simulator with new emerging technologies like phase change memory and STT-RAM after the paper was out throughout the last 10 years, let's say. And it also provided support for new proposals, as I explained. And at the time of the study, it was faster than the fastest open source simulator. And you can see that it provided fast simulation of these DRAM standards compared to the others existing simulators. So one of the unique case studies that it enabled was the comparison of DRAM standards. Again, we covered it, so I will be very quick. But this was not possible before because none of these existing simulators had support for this many DRAM standards at the same time. And we were able to compare their performance across 22 workloads using a simple CPU model, showing different trade-offs with different workloads, comparing different standards to each other. So if you were to do a study on a specific type of workload, you would be able to see which DRAM standard you would get more benefit compared to the other ones. And this was something new at the time. So Ramulator is open source, and you can check our GitHub repo and use it. And we also value reproducibility a lot. So we included some instructions to reproduce the results that we have shown in the paper. And you can follow these to get the same results, get the same figures, and so on. It is also possible to integrate Ramulator with other simulators. Here again, you see some instructions about integrating it with Gen 5, which then would be providing a more sophisticated core model that can be used as front end to Ramulator, and you would still get the detailed simulation, memory system simulation coming from Ramulator. And this was used by many works again in the past. So Ramulator enabled many works from different research groups, from different industry companies, and we were able to expand it with the feedback that we gathered, with the observations that we gathered, and we are still maintaining, and it's still in a good place. But we wanted to extend it even more. We wanted to improve it, and this is why we developed Ramulator 2, a modern, modular, and extensible DRAM simulator, which was published in Computer Architecture Letters in 2024. So the motivation behind is that, again, DRAM and memory control landscape is still changing, but we wanted to focus on two lines of work that we were actively doing. First one is basically we were looking into robustness issues in DRAM, from data retention to read disturbance like RowHammer, rowpress, column disturb, and so on. And some of these works we have covered so far. And we wanted to basically improve the simulator to give us what we want, easy simulation in terms of these studies. And we were also doing a lot of work in performance issues, alleviating performance issues in main memory system. For example, we were designing processing in memory architectures. We are still designing these. We are still doing active research on these topics. Basically, we wanted to evaluate different architectures. We wanted to look into emerging memory technologies to see their trade-offs. And we wanted to combine these two lines of works to evaluate the performance overheads of read disturbance mitigation mechanisms, and we wanted to do them in a very fast manner. So we wanted to be able to extend the simulator with new ideas, with new mechanisms, but we want to implement them very fast. And to do so, a DRAM simulation infrastructure was very much needed to understand, to characterize, and evaluate the robustness and performance of DRAM. So we developed Ramulator 2, modern, modular, and extensible DRAM and memory system simulator. Ramulator 2 models a wide range of DRAM standards and memory controller functionalities similar to Ramulator's first version. So we kept the ability to perform studies across different DRAM standards. We also expanded the memory controller functionalities and so on. And basically, Ramulator 2 has a modular and extensible software architecture, which I will talk about and highlight what it gives us, like what kind of benefits. And it also enables us to do fine-grained modeling of DRAM operation at a cycle level. This means that when we want to simulate a DRAM operation, a DRAM command, we can do this at a very high detail level. And again, Ramulator 2 is used in a wide range of research works. Even though it is pretty new, it enabled a lot of works in the past couple of years. So I want to now talk about Ramulator's design and some features. The first thing that I need to talk about is the hierarchical state machine-based modeling of DRAM that we enable with Ramulator 2. Here you see a graph with some nodes. Some of them are labeled as channels, ranks, bank groups. And if we were to expand this graph, we would see banks and rows as well. So these are all hierarchical levels of like parts of organization of DRAM, and we model each of them as separate nodes in this graph that are connected to each other with different relationships. For each of these nodes, we basically maintain a state of this DRAM node, including current state, such as it is opening, it's closing, or activating, it's open, close, or activating, based on the last commands that we have executed for that node so far. And we also have the information of some timing constraints, such as earliest time in the future that each DRAM command is allowed to be issued to that node, such that we can maintain correct operation, considering the timing constraints that we have, timing parameters that we have in DRAM. We also store some information about the energy and power statistics, like the time spent in each state and the number of DRAM commands that are served in that node so far. And this information that we hold, we store, we can basically feed it to another model, such as DRAM power models, to evaluate the performance, power and energy consumption of our system. And this state of the DRAM node, can be extended to include different functionalities, different statistics, and basically based on what you want to implement in your architecture, you can have different kind of states. For example, if you are introducing new states, you can add them. So DRAM commands are implemented as lambda functions, and we basically hierarchically traverse and update the state of the nodes based on when we are performing these commands. So the first thing that we do is we check the current states of the nodes to decode which DRAM command to issue. Let's say that we want to send a memory request, read request to the memory, we first need to check if that row, the target row, is open or not, right? And based on that, the DRAM commands that we will issue will change. And we basically first perform these state checks. After that, we programmatically apply the state changes that are coming from the executed DRAM command, such that if we open another DRAM row, the state of the row node will change accordingly. And after that, we updated timing constraints and power metrics to maintain the state of the DRAM nodes and basically maintain the correct operation. One thing that is important is that we have a template library of generalized DRAM commands, such as like Lambda functions, which allows us to reuse the command implementations across different DRAM standards. Here you see an example of function that is named require all banks closed. What it does is that, as you can see, it traverses all through all banks and checks the states. And if a bank is not closed already, it says, it basically returns a command that is precharge all banks commands. So it ensures that all banks are closed. This is pretty simple, but it is also required in all of these DRAM standards that you see on the side of the slide. So having a library, generalized library, allows us to reuse this piece of code in wherever we need to use it. And we don't need to rewrite it. We don't need to make the effort to come up with a way to implement this. And as you can imagine, there are many such functions in our simulator that really makes it very easy for us to implement new specifications. So whenever you're trying to add a new specification, a new DRAM model, you can just use these functions that already exist in the source code, and you can focus on the new functionalities that you want to enable. And this really makes it very easy to extend. I will now talk about the modular and extensible software architecture. What we mean by that is that all components in the memory system are modeled with the same interface and different implementations. For example, let's say that we have our memory controller. The memory controller has different components, such as the address mapper, request scheduler, refresh controller, role policy, and so on. So all of these components work together, and they need to communicate with the memory controller. So our software architecture looks something like this. What I want you to focus on here is the gray boxes that are interfaces. And you can see that the front end is there, memory system is there, address mapper, controller, and so on, until we reach memory controller plugins. So our architecture defines the functions that these components, these interfaces talk to each other. So we define how they can interact with each other. And what this allows us to do is that we can flexibly change one part of the architecture. Let's say I want to change the request scheduler. I want to change FCFS that is implemented here. I want to make it first come, first serve. I can do that without changing the other parts of the architecture. And this basically gives us the flexibility to change different parts without rewriting the memory controller every time. A good example of this is the plugins. So the memory controller plugins are very useful for our research, for our active research, because this is how we implement the read disturbance mitigation techniques, for example. It can be used for many things. It can be used as loggers. It can be used to get statistics in the system. But basically, what I will focus on here is the read disturbance mitigation mechanisms. Here you can see that the plugins interface, or basically the way that it communicates with the DRAM controller, is fixed. You can see that in the orange line, the DRAM controller, memory controller, can update the plugin with issued commands. This means that the plugin will know whenever DRAM controller issues a command and can take actions based on that. So the plugin itself can, for example, update some metadata tables, update some counters if we are counting activations, for example, and then can return a request to be issued in the next cycles to the memory controller. And this allows us to send preventive refreshes back to the controller such that it will perform them after the plugin tells the controller to perform them. So this allows us to basically define the way the plugin communicates with the controller. It gives us some ability to enqueue different requests. And the actual implementation of the plugin is independent of that. So we decouple the implementation and the communication. And what this helps us do is that we can implement as many read disturbance mitigations as we want, and we can also implement as many request scheduler mitigations as we want. And this allows us to basically define the way the plugin communicates with the controller. And the actual implementation of the plugin is independent of that. So we decouple the implementation and the communication. And what this helps us do is that we can implement as many and we can basically change just the implementation without changing the memory controller for the most cases. So there are more details in the paper, basically more detailed explanations of the Mutlu methodology. We describe how to write new DRAM specifications. We talk about, again, adding memory controller plugins or RowHammer mitigations, and there's also a performance comparison with other DRAM simulators. I will now talk about some case studies. The first one I want to talk about is actually included in the paper itself. So we basically evaluated 6 different RowHammer mitigation techniques for this case study to compare their performances at different vulnerability levels. So in the figure here, you see on the x-axis, we have a lot of different RowHammer thresholds. And on the y-axis, we see the normalized weighted speed up. Basically, what this allows us to do is that we can see at each vulnerability level which mitigation performs compared to each other. And the important part is that we implemented all of these RowHammer mitigation techniques as plugins to the same memory controller implementation. So we again changed just the plugin part without hard coding the memory controller side. The ideal case here is, I think, per row activation counting, because it's like the ideal tracker. So you know the exact activation counts. But it also incurs some performance overhead because it needs to do preventive refreshes. So the next case study basically builds on top of this one. So between these 2 case studies, the JDEC DDR5 specification was updated with per row activation counting, or PRAC, which we talked about when I presented RowHammer. What it does is it adds per row activation counters inside the DRAM and defines a new signal for the mitigation to send to the memory controller to say that I need some time to do preventive refreshes. So this changes the communication between the controller and the plugin a bit. And this is why we extended the memory controller implementation with this behavior. And we were again able to simulate it and evaluate it very fast using the same and comparing it to the same implemented mitigations that we had in the simulator. And this was published in DRAMsec in 2024. Building on top of this, again, we talked about Cronus a bit. Based on the observations that we gathered in the previous case study, looking at PRAC and how it performs in different levels of the vulnerabilities and so on. So we were able to solve 2 major drawbacks of PRAC by implementing a new mitigation technique on top of what we had so far. And we were able to, again, compare it against all existing mitigation techniques very fast. And it was also published in HPC 2025. So these were a few of the case studies that were enabled by Ramulator 2, but there are many more other works that use Ramulator 2. And I want to highlight some integrations that also enabled some of these works. So the first one is that we integrated Ramulator with Gen5, which again gave us a more detailed core model coming from the Gen5 side. And we also maintained the Ramulator 2's detailed memory system simulation. And we used this to do this study on understanding and mitigating covered channel and side channel vulnerabilities introduced by RowHammer defenses. So in this study, we introduced demonstrated side and covered channels, leveraging 2 latest industry solutions to RowHammer, which were already implemented in Ramulator's source code. And we evaluated new defenses against TCuARCH, again, implementing them as plugins. So we were again able to evaluate this very fast. And we were able to get the benefit of Gen5, having the front end from the Gen5 side to execute binaries instead of traces, and again, have the detailed simulation memory system simulation coming from Ramulator. And we have also another integration, which I think Konstantinos will talk about more. So it is also possible to integrate Ramulator 2 with Virtuoso to enable fast and accurate virtual memory research with imitation-based operating system simulation methodology while having benefits of Ramulator. So I will quickly describe what is the benefit of doing so. So we can enable fast and accurate evaluation of the hardware and software components of the virtual memory subsystem with low simulation time and memory overheads when we combine these 2 different simulators. And an example of a case study that we can do is we can evaluate page fault handling Here you see on the bottom side the Ramulator and the Ramulator side, and on the top side the example user space kernel is coming from Virtuoso. So basically, by making these two simulators communicate with each other, we can simulate page fault handling and the memory requests that are coming from that in the Ramulator side. And we held a workshop at Micro, which again talked about this integration a bit more, and mostly focused on the use case of enabling swap space studies. And you can follow this tutorial from this watching this YouTube video, and there are some timestamps that you can see here that will take you to the use case with the Ramulator. Okay. So now I'm going to talk about a bit about the validation of Ramulator 2. We initially validated the command traces, DRAM command traces that are coming from Ramulator 2 against Micron's DDR4 Verilog model. Micron is a DRAM manufacturer, so we trust them to, sort of have the correct command traces. So we basically evaluated Ramulator with streaming and random access patterns with varying memory intensities, and we found no timing or state transition violations, meaning that Ramulator 2 was generating DRAM command traces that were consistent with Micron's Verilog model. We then did a study on comparison against real systems, sort of inspired by recent work, the MES paper which I will call it. Basically, this work was aiming to compare the accuracy of the memory simulators, including Ramulator, against real systems. To do so, they used latency bandwidth curves, which I will again explain here. On this figure, on the x-axis, you see the used memory bandwidth, and on the y-axis, we will see the memory access latency. And the latency bandwidth curve looks like this. As we go from the beginning end here to the end of the curve, what happens is that we increase the memory intensity. We basically perform some memory requests, memory operations, and we increase the memory intensity such that we have little gaps or no gaps in between the memory requests. And this results in mostly increasing the memory bandwidth that is used. And we see higher memory access latencies because of the contention that is in the system. And they basically evaluated varying read-write intensities, gathered a bunch of different curves, showing like different ratios of latency bandwidth curves were yielding different memory access latency characteristics or different used memory bandwidth characteristics and so on. And they evaluated a real system with this evaluation methodology, and these were the curves that they were getting. And as you can see here, I think here the darker lines correspond to having more writes in the ratio, and the lighter ones are, for example, the lightest one is all read requests. And as you can see here, as we go to the higher memory intensities, the memory access latency increases, which is what's expected because you will get more contention. And at some cases, this results in some lose in the memory bandwidth due to the DRAM bus turnaround latency. And these were the results that they claimed to be obtained with Ramulator 2. So these were their claim results for Ramulator 2. As you can see, these two are not that similar to each other. And we were basically intrigued by this result. So we wanted to understand how this would happen. And we looked into, basically the paper also contended that Ramulator 2 poorly resembles the actual system performance, which was also shown with their claimed results. And we were intrigued by this because we wanted to understand how this happens, why this happens, and how we can fix it if that's the real results, that's the results that we would get. So we wanted to reproduce the results. And we looked into the paper. We basically had a detailed pass over the paper. And also we looked at the artifacts as well. And we were not able to reproduce the results. So we communicated with them. We had a nice communication. And in the end, we realized that the results claimed by the MES paper poorly resembled the real system results due to the major configuration errors of Ramulator 2 evaluation that they had. So now I will explain what went wrong. So we identified multiple trivial human errors in the configuration of Ramulator 2 as described in the MES paper and as obtained by our communication with them. The first one is that they were configuring Ramulator with half of the channels of the real system. They were extrapolating single-channel DDR5 results to 8-channel DDR5 results instead of 16 channels that they had in the real system. And this is why they had this huge gap between the memory bandwidth that is achieved by Ramulator. And this is expected because if you have half the channels, you have half the bandwidth, so it's straightforward. The second issue was that they were also hard-coding cache configurations in Ramulator, which then led to significantly smaller DRAM round-trip latency and significantly lower queuing delay. And they were also pointing out that compared to the real system, Ramulator showed low memory access latency as well. So these were the two reasons why the results were not matching the real system results closely. So we also basically identified a lot more issues with the paper, with the evaluation methodology, and you can find all of those from our paper on arXiv. So we then decided to produce our own results. So we configured Ramulator 2 correctly and evaluated the same access pattern that they described in the paper. And these were the results that we were obtaining. So as you can see here, these results make much more sense starting with. And they also show that Ramulator 2 can get very close to the maximum achievable bandwidth when the read ratio is 100%. And as we increase the write ratio, we see some gaps, which is again expected, and it is also shown in the real system results as well. So these results more closely resembled the real system results. So we conclude that when correctly configured, Ramulator 2's simulated memory system performance actually resembles the real system characteristics. So that was one of our conclusions, but we also had some other analysis about other results that were presented in the paper, and all of those can be found in our paper. So we also open source this to be able to others to be able to reproduce our results to help them. And there are also some steps to reproduce all results and figures in our paper. So maybe it is good to again highlight how to use simulators correctly and in true open source spirit. We already covered so far like how to use simulators, how to correctly configure them, and I also demonstrated the impact of not correctly configuring them, I guess, a bit. And it is good to think about how to use simulators correctly. So first thing first, basically we need to know the simulator that we are using. We should not use it as a black box, meaning that if you are getting some results using some simulators, it is basically good to understand why we are getting those results. If you are expecting different results, we should be able to explain why we're getting some different results from the expected ones. If you don't know the simulator that we are using, it is very difficult to understand and also make observations about the system that we are simulating. You should also know the boundaries of what each simulator is capable of and also be ready to extend it for our purposes. There's a high chance that the simulator that we want to use is not doing whatever we want to evaluate, or it can be very close. It can be, basically you can do some hacking to go around and change some parts to get what you want, but it is also a good practice to extend these simulators and to improve them, to basically also ensure that whatever you're evaluating is whatever you want to evaluate in the end. We should always configure things correctly, as also demonstrated by the results that I showed you just now. There are a few helpers in that case. There's almost always documentation. And in the case of the results that I showed, basically the documentation of Ramulator 2 correctly show that the bus width of a channel is something else than what they assumed. And this was the main reason why they obtained such different results. And documentation could help with that. And it's also good to check other open source example use cases. There are many projects out there that are using simulators that probably you want to use. And it is always good to check how they configure their simulators to get an idea about it. And if all else fails, if we really need to, I guess, we can always ask for help, especially from the developers of the open source code or the authors of the related paper, such that they would be able to point out misconfigurations or different usage or unintended usage in your evaluation. And they can help you basically correct these misconfigurations, get reasonable results, ideally before you publish your results in a paper. And lastly, we should always respect open source development. So these tools are developed and maintained freely for the benefit of the scientific community, meaning that we open source these to aid future research, and we hope and believe that it will help other researchers. And it again really takes some time to debug stuff and make sure everything is working correctly, and answer some issues and so on. So we should all be respectful to each other. There are a lot of good tools out there that are maintained by very busy people, and it's good to also respect their time as well. Okay, to wrap things, again, Ramulator 2 has already enabled many works that are, some of them are listed here, and it's a growing list. This is probably even now outdated. I will update it. And basically, I can conclude this part of the talk. So we, again, developed Ramulator 2, which has fine-grained modeling of DRAM operations. It models a wide range of DRAM standards and memory controller functionalities, and is, again, used in a wide range of works. We're interested in expanding this, extending the scope of Ramulator 2. We have some ongoing and future works in that regard. So we're interested in adding unit and regression test coverage. We are doing some work on adding more DRAM standards and emerging technologies. We're interested in having a more detailed memory controllers modeling, and also implementing some processing in memory architectures. And if you think these are interesting, you can always contact me and we can work on it together. Okay, let me conclude my talk. This was Ramulator. Again, if you want to use it, we are happy to support and help anyone who wants to use it. And if you want to improve it, I would be happy to discuss more. Thank you for listening. So basically, on-die ECC can have like different implementations. If you know what you would implement as the error correcting mechanism, we can implement it in Ramulator. I think, again, as a plugin even, but you might need to change the nodes a bit. But yeah, I think that's very interesting. If you are interested in having like some error model, that's a different story. So you would need to get some characterization data to actually have an idea about like what would be the errors that I would see. And then based on that, you need to combine it with the ECC, I think, if that was your question. So for our studies, especially the read disturbance mitigation techniques, we're not getting results regarding latency or area cost from Ramulator itself. Ramulator is mostly used for performance analysis, energy consumption analysis regarding DRAM. I think it is best to use the tools that are designed to capture latency or like estimate area overhead would be better to use instead of Ramulator in that sense. But you can again like maybe guide your implementation for these other tools that are doing the area evaluation or latency evaluation by the implementation that we are doing in Ramulator. That needs to be basically both implementations or designs should reflect each other. But I wouldn't suggest you to basically extend Ramulator to do latency studies because it might not be that accurate without proper effort. Do you need a microphone? I can give you.
Is there another one?
I think.
Oh, wow.
That's a.
Okay, I think Nisa did a great job explaining things. Can you go back to that slide where you have? Yeah, this is good, I think. I like this. Yeah. So we have developed a lot of open source code. We released it online. A lot of people use it. A lot of people appreciate it. And it's all maintained for free. These people, Nisa, Haosong, Ataberk, none of these PhD students get paid extra for maintaining the software. Our goal is to advance science and make it better for everybody to use. Make life better for everyone, basically, advanced science. The Ramulator enabled a lot of studies. You can see there's almost 1,000 citations. I'm not a believer in citations because if we did Ramulator for AI, we would have gotten 20,000 citations by now, probably. But 1,000 citations in a field like this in 10 years is a huge thing. And people have actually used this in many good ways, in my opinion. If someone finds a bug, the right way to deal with that is to report it to the people, because that bug may not be a bug. It may be your own error, like in this case, what happened with this mess paper, which I would encourage you guys to read, and I would encourage you guys to read the cleaning up the mess paper afterwards. The solution, the issue here is not that they wrote a paper about it. The issue is basically they never contacted any of us before writing a paper about many simulators and claiming very false things in that paper. And one interesting thing is this paper was artifact evaluated and it actually got all the artifact badges. We don't know how. Maria probably can tell you if she knows how. I don't think she knows how because she actually did a lot of work on trying to figure out, replicate these mess results, but we weren't even able to find the simulator that is supposed to be available, let alone reproducible. It's not even available. And somehow they got an artifact evaluation badge. So that's another issue, but that's a separate issue then. If you're using a simulator, know what you're doing, basically. And if you don't know what you're doing, contact the authors. The authors have no reason to respond to you, first of all. That's the first thing, because this is done all in free time. Some people graduate, they're gone. What do you do in that case, right? Ramulator is not as well maintained today. Ramulator 2.0 is maintained. So this is all free open source software. You're not buying the software from someone. Even when you buy, actually, you get a lot of bugs. Have you ever used Microsoft Windows, for example? You see what I mean, right? So basically, I think in scientific literature, it is very horrible, in my opinion, to do things like this. And what is worse is actually, if you read our paper, cleaning up the mess paper, we actually tried to reason with these people who wrote that paper, and we tried to get them to fix the paper, but they gaslighted us. I like the term gaslighting. This is, I'm adapting to the times. They gaslighted us saying that, oh, we're harassing them or something like that. There's no such thing. We were trying to correct the scientific record, and they were not amenable to correcting the scientific record. And as a result, we have the cleaning up the mess paper. I'd really recommend you guys to read Cleaning Up the Mess paper that is out there to correct the scientific record. And hopefully you don't have to deal with things like this. because our goal is to advance science. And if you want to advance science, you actually do it by being open and talking with the people who do good work. Okay, I'll leave it here, but I hope some people learn their lesson and they don't continue doing bad research. All right. And I should also say that, I should also say that this actually took a lot of toll on people who are co-authors of the Cleaning Up the Mess paper. Hao Song, Atabak, Maria, who's in the back, Nisa, Elibet Geraldo, and Giray. They actually did a lot of work to do what this mess paper authors should have done in the first place, which is verifying their simulator, which is verifying how they simulated the thing that they simulated and how they produced the results that they produced. Basically, they did all the work that paper should have done, so maybe they should have gotten the best paper runner-up award with the Cleaning Up the Mess paper, you know. They did more work, I would say. And this takes away from the time that they're doing work on their own research, because these people have their own research that they're working on. They don't have to rebut a crappily written paper like this. So we're discussing this because this actually gets into scientific progress quite a bit. And all of this should have been easily solved if the previous paper's authors were actually contacting us before the paper was published. And even after the paper was, after we actually asked them, what's going on? Let's take a look at your results. They could have worked with us to actually correct the scientific record without us having to write a paper like this to actually correct the scientific record. So thank you guys for doing the right thing for science. Even though this took away from some of what you did. I know Hao Song was actually going to submit multiple works to ISCA. He got delayed quite a bit. He was on an internship on top of this. Atabak is also on an internship. They're still on an internship. They actually put a lot of time into it to correct something that was really poorly done. Okay, we're going to put this as part of the homework reading. We're going to put the mess paper also. Why not, right? And then you can actually compare and you can make your own decision because it's out in open science right now, right? And we're happy to put the email conversations also, if necessary, as an appendix to this paper. No problem. They're all there, including the last email, which is really gaslighting us. Okay, you get good stories if you come to my class, see? Okay, all right. And if any of those authors are listening, only thing they need to do at this point is apologize. But that takes a lot of courage to apologize, actually. Okay, anyway, now we got to move to other slides. Okay, you know where this is? Let me get some water. All right, thank you. Oh, you need to do something? Oh, in Zoom, yeah. Oh, I should have done that. Okay. Okay, thanks, Nisa. Zoom decided this annotate thing is very useful, apparently. Okay. Okay, I'm going to get started on prefetching. We're clearly not going to cover everything in prefetching, but this is such an important topic. And again, we've been doing research on prefetching from my graduate student days. My first internship at Intel in 2000, May to August 2000 was on prefetching. I actually went and tweaked some of their prefetchers and got my first patent on throttling the prefetcher based on how much bandwidth you have available on the front side bus. At that time, it was the front side bus. There was memory controller was not on chip actually. So this is a topic that's also close to my heart, like many of the topics. And this is such a critical topic that we had to cover it It's a lot of fun also. And there's a lot of fundamental contributions to be made in this area. Rahul just finished his PhD thesis working on prefetching. And Genome also helped Rahul on one of the latest papers. Maybe they can talk about that when the time comes. But there's a lot more to be done in this area. So this is going to be a processor-centric view, actually. Although prefetching can be applied in memory-centric systems also. So it's a topic that is going to be pervasive. So, okay, we're going to cover a lot of things. Let's see, probably at least 1.5 lectures. We're going to look at basic prefetching techniques. We're going to talk about how to evaluate and control a prefetcher, and talk about more advanced prefetchers, and maybe talk about issues in multi-core, etc. So essentially, prefetching is trying to target the memory latency problem. And you have seen this problem before, right? You have seen several pictures like this. Okay, this is a bit slow. And we've covered this, so I'm not going to cover this in detail. But memory latency has not been improving as much. This was 18 years time frame for DRAM. This is actually a longer data sheet that I actually showed. This is data sheet examined from 1970 to 2024. One of my other PhD students, Minesh Patel, who's an assistant professor at Rutgers right now. But essentially, according to that study, we've observed over the course of 50 years, you have 1 million X capacity improvement, but latency has improved by only 8X. And in the most recent 25, 30 years, it has not improved that much, as you can see. In fact, some latencies have gone up. So that's interesting, basically. And we have discussed why this is the case in earlier lectures. Part of it is a design choice, clearly. Capacity is more important for this sort of business. And capacity is also more important from the perspective of processor-centric folks in general. And latency is harder to improve than capacity in general. So there's no question about that. Also, there's something fundamental. But I would recommend you to take a look at this paper that Minesh wrote, which is actually a really nice overview of the DRAM and controller area with a lot of analysis of real data sheets. So if you want to actually look at the trends of what has happened to DRAM in the last 50 years, this is the most up-to-date paper that you can find. Okay, latency is critical for performance for many workloads. We've seen that. And we also covered this paper that I just talked about in the Ramulator lecture, or in the simulation lecture, which looked at latencies, the effect of latency on some workloads, and said basically, because some DRAM types increase latency, they're not good for performance, essentially. Even though they're newer DRAM types, because they lead to higher latencies, they actually don't improve performance or reduce performance. Because the trade-off they're making is they have higher latencies, but they also provide higher bandwidth. But some workloads don't benefit from the higher bandwidth unless they're rewritten to exploit the higher bandwidth. But they get degradation because the latency has increased because of the new DRAM type. So that's also a nice paper that we have discussed. So how do you handle latency, essentially? So there are multiple ways of doing it. One is fundamentally reducing latency as much as possible. I call it latency reduction. The other is hiding the latency seen by the processor. And the other is tolerating the latency seen by the processor. So reducing latency is a data-centric approach. We have seen this. I don't know if these link to this year's lectures, but I haven't checked that. Anyway, it doesn't matter. There's some memory latency lectures that we have delivered at some point. We looked at how to reduce the memory latency on the DRAM side with techniques like AL DRAM, TL DRAM, etc. We talked about the other approach is hiding the latency. This is more processor-centric approach because you design a processor may be far away from memory or near memory or inside memory. It doesn't matter. You can employ caching or prefetching. Caching is one way of actually reducing latency, right? Or hiding latency. The latency is there when you fetch the data for the first time. You incur the latency, but if you need it the next time, it's in your cache. Right? And then tolerating latency seen by the processor is also a processor-centric approach. And multi-threading, out-of-order execution, and what we're going to cover, run-ahead execution, are techniques that can tolerate the latency or amortize the latency seen by the processor. So today we're going to talk about prefetching. But again, this is actually a slide from my own PhD proposal. In 2003, I made this slide. I still like the slide. But basically, these are conventional latency tolerance techniques: caching, prefetching, multi-threading, out-of-order execution. Essentially, these are techniques that all have upsides and downsides in the end. They are widely used. Actually, all of them are very widely used in today's systems. And they were all invented early in 1960s, if not earlier. But these are the original papers. Actually, Wilkes is not the original paper. There's another paper that we have. But yeah, anyway, it doesn't matter. And they sometimes work, they sometimes don't work. So today we're going to focus on prefetching, and we're going to see that it works nicely for regular memory access patterns, but irregular access patterns are hard to cover. But we're going to look at that also. Okay, so these are some links to some lectures if you're interested, because we're not covering everything clearly in this class. Out-of-order execution, we're not covering, for example. Okay, let's jump to prefetching. So what's the idea? The idea is very simple. You fetch the data before it's needed by the program. It's called also preloading or prefetching. You can actually see prefetching, preloading in some of the earlier papers. Instead of loading, you preload, right? Load instruction, you have a preload instruction or some hardware doing this. So why do you want to do this? Because memory latency is high. If you can load the data early to a buffer or to the cache that's closer to the processor, you can reduce or eliminate that latency. Hope is that the processor will not see that latency ever. It can eliminate compulsory cache misses, meaning cache misses that you're seeing for the first time. A processor is touching an address for the first time, right? You may be able to prefetch that. Why? We will see soon, basically, because it may be part of a pattern that you predict, right? It can eliminate all cache misses, actually, if you are able to design a prefetcher like that. Basically, if your cache is small, no worries. Keep prefetching into the cache the right things at the right time and use the cache as a buffer for prefetching. If your cache gets conflicts, no worries. Figure out those conflicts and prefetch data early, right? If you can do it. Coherence, we're going to talk about later, but coherence is someone else actually invalidates the data because they're writing to it, and you have a shared data across different caches. Again, if you can predict that you're going to access that data, you can prefetch it to your cache. It becomes harder, of course, if you have more causes of misses. And the key is predicting which address will be needed in the future. But this is not enough, as we will see, right? Which address is part of prefetching. And it works if the programs have some sort of predictability in their address patterns or misaddress patterns or access patterns, let's say. Okay, so prefetching actually doesn't impact correctness, meaning you can prefetch some data that is wrong, and that data is simply not used. That's the idea. It's a speculative execution method, meaning speculative execution means you do something before you know that thing is needed, right? So essentially, we're doing something before we know that that data is going to be needed from that address. So we bring that data into the cache or some buffer, and if the processor never touches it, the data remains there. At some point, it gets evicted, right? So it doesn't affect your correctness in the end. You don't need to go and evict that data, right? So there's no need for state recovery. This is very different from branch misprediction, right? In branch misprediction, you mispredict a branch, you're on the wrong path. You have to do something to get onto the correct path, right? Otherwise, you'll be on the wrong path and you will never get the correct result of the program unless you're lucky that the wrong path doesn't affect your results. And maybe, yeah, there's actually a paper that shows that. This was written in 2004 in PACT, I think, by Sanjay Patel's group. And the idea is a fraction of the branch mispredictions don't matter. You don't need to recover from them because it doesn't affect the output of the program. That's interesting to think about, right? This could happen because you may be doing some optimization in the program that's really not affecting the output. Think about compilation, for example. You're running GCC. It's compiling a program, and it's having some passes. And those passes are not really affecting the output, which is really the optimized program, for example, right? So algorithms may have tolerance to branch mispredictions, but you don't want to count on that unless you absolutely know things. So basically, prefetching doesn't affect correctness, but I mean, it may affect actually security, side channels. It's good to think about that these days, because when you prefetch data, you're bringing something that you're potentially not supposed to bring. And that may actually leak some information to some other observer program that may be around. And you've seen some example from Nisa's earlier presentation with RowHammer. That was a memory site side channel, right? Because of RowHammer protections. But you could also have side channels because of prefetcher actions. Okay, so in modern systems, prefetching actually happens at the cache block granularity. You basically prefetch a cache block. If you have sub-blocks, you can prefetch smaller parts. And it can reduce both miss rate and cache or miss latency. It can be done by the hardware compiler programmer system. Everybody can do prefetching, basically. And in fact, systems like operating system can do prefetching, right? I think Windows was one of the earliest operating systems that employed machine learning techniques to decide what programs to prefetch when, based on the usage patterns of a person who's using the computer. So they would try to learn at this point in time on Tuesdays, 9 a.m. in the morning, this person who's using this computer loads program X. So let me actually prefetch the pages for that program X into the main memory. Right? This actually was really implemented, and I think that was one of the innovative things that was done in Windows as early as like 2006, 7, etc. Okay, so that's an example of system level prefetching. You could do it at the distributed system level. Programmer can decide what to do. Okay, we're going to look at some of these things. We're going to focus on especially hardware. So this is my picture from a paper that I wrote in 2005 on prefetching. We were looking at actually reducing the pollution caused by speculative prefetch references. And this is one example of where Prefetcher, okay, I guess I got to use this one, where Prefetcher may sit. So you can see that this is an old picture because this is the chip boundary. The bus's memory controller is not on chip. Memory controller used to have its own chip in the past. Okay, this is an example of Prefetcher. It observes here the requests that are coming into the L2 cache and also requests that are missing in the L2 cache. It basically records some addresses and tries to figure out a pattern out of what the processor is accessing. And then it generates some prefetches based on that pattern and inserts them into the L2 request queue. So this is one design choice, right? You could also have a prefetcher for iCache, for Dcache. Another prefetcher may be observing what's happening at the memory controller level. And in modern systems, actually, there are prefetchers at every level almost. I don't know exactly how many, but more than 10 prefetchers exist in a modern processor, some modern processors. Is that true? Yes? Yeah? Okay, 2 plus 3 is 5. Not enough to make 10. What about memory controller? Anyway, maybe you obtain that information from a core designer who doesn't know what goes on the memory controller. You know, that also happens. And that's a real problem, actually, because there's a prefetcher in the memory controller that's designed by whoever designs the memory controller, and there are prefetchers in the core that is designed by whoever designs the L1. There's a prefetcher in L3 who designs the designed by someone who designs L3, and these all are supposed to work together nicely. Good luck. Yeah. Okay. But yeah, imagine having prefetchers all around, because this is such a big problem, basically, and everybody wants to tackle it. And having these boundaries within a company also doesn't help, basically, like I said. But it's good to think about these. Okay, so there are actually many interesting questions in prefetching. All of these are research topics also today. What do you prefetch? When do you prefetch it? Where do you prefetch? And how do you prefetch? And where has multiple topics also. Where do you prefetch into? Where do you do the prefetching, etc.? Okay, let's cover some of these. So what means what addresses to prefetch, which is your address prefetch prediction algorithm. When means when do you initiate a prefetch request? Are you going to be early? Are you going to be late? Are you going to be on time? On time is a good idea in general, just on time actually, before the processor needs it. Yeah. And where do you prefetch? Where do you place the prefetch data? Do you put it in caches? Do you put it in a separate buffer? Where do you place the prefetcher? Which level in the memory hierarchy we just discussed? Maybe everywhere. If the answer is everywhere, how do you coordinate between them? And how does the prefetcher operate and who operates it? And there are many modes for this: software, hardware, execution-based, cooperative, hybrid, etc. Okay, so let's tackle some of these things before we go into prefetcher examples. What addresses to prefetch? Essentially, you don't want to prefetch useless data because this wastes resources. Even though it doesn't affect your correctness, it wastes your resources. Some very important resources potentially, memory bandwidth, for example. This directly affects your energy, of course, because you're putting out addresses and getting data from, basically you're moving data, right? An unnecessary movement of data is not good. Even necessary movement of data is not good, since you've seen all of the memory-centric lectures that we have, right? We don't want to do it unnecessarily. Memory bandwidth, it also uses cache or prefetch buffer space. And if you don't actually waste space, you could all utilize these for demand requests or more accurate prefetch requests. So accurate prediction of addresses to prefetch is important. This is one metric to evaluate a prefetcher. We'll see more metrics. Prefetch accuracy is the number of used prefetches divided by the number of sent prefetches. We're going to see that again. So how do we know what to prefetch? Basically, there are multiple approaches to this. And we're going to see many approaches. One common approach in hardware prefetchers is to predict based on the past access patterns. You see some access pattern, and you try to memorize or find something inside there. This could actually use machine learning, as we're going to see. That's one of Rahul's works. Or you can use the compilers or programmers' knowledge of data structures to do more informed prefetching. And we have actually done work in that area also. This is a bit harder to do. Yeah. And in the end, you design some sort of prefetching algorithm to determine what addresses to prefetch. This is a good time to think about what are predictable address patterns. If these are the cache block addresses, you're accessing cache block A plus 1, A plus 2, A plus 3, A plus 4. You can predict what comes next, right? A plus 5, A plus 6, A plus 7. So this is called a stride. The stride is 1 at the cache block level, cache block address level. So a prefetcher can learn the stride or memorize the stride. Of course, this works nicely until the processor stops accessing in a strided manner, right? So the prefetcher starts prefetching. It says, oh, the processor is going really well. The stride is 1. I'm going to prefetch from A plus 5 to A plus 255. And the processor doesn't access anything after A plus 4. Then the prefetcher is wrong, right? And you prefetch a lot of useless stuff, believing that this pattern will continue. So when does a pattern stop is also important. Okay, that's an easy one. This is also an easy one. Here, the stride is 42 as opposed to 1. Here, there is no stride, I guess. At least there's no single stride, right? If you look at, this is also predictable though, I think. Let's see. So yeah, plus 2, plus 3, plus 4, plus 2, plus 3, plus 4, plus 2, plus 3, plus 4. This is a bit harder to detect. You need to basically correlate the strides. So after plus 2, you see plus 3. After plus 3, you see plus 4. After plus 4, you see plus 2. So you can actually do that. And you can use the correlation using either a single one or 2 or 3, whatever. Basically, this is predictable, as you can see, right? This is another one, a bit tougher. Assume that there is no close relationship between these addresses. There's some predictability here, right? For example, Y is always follow after X. So maybe you can figure that out. What else? And T comes always after Y, I guess. Yeah, so X, Y, T is repeating. I figured it out. I have a good pattern matcher here, at least for this task. See, this is what machine learning does, matching patterns. Okay. Okay, I don't know. Do you guys have a good pattern matcher for this one? This is a little bit different. So the base is A, and based on that base, you always do, regardless of the base, you always do plus 1, 67, plus 67, plus 18, plus 7, plus 99, right? So this is a different kind of prefetcher, potentially, to capture this sort of pattern. So hopefully this gives you an idea. Basically, you need different types of prefetchers for different patterns, right? Or some general pattern detector that works for all of the patterns. So what people aim for today is, for hardware cost reasons, you don't do the general one. You really have these specialized, more specialized prefetchers for different types of patterns. Okay, Rahul has worked on something like this, so ask him. Is that true? That's not part of your thesis, though. Okay. Is this any good right now? This patch? Okay. Okay, maybe you can talk about it. This was published in 2019, before Rahul was a graduate student. Okay. Okay, that was what. And I could keep going and we can have fun, but let's move to when. So when to initiate a prefetch request. So if you prefetch too early, prefetch data may not be used or demanded by the processor before it's evicted from the storage, buffer, or cache. Right? If you're too late, you may not hide the whole memory latency. And there's, of course, anything in between, right? Ideally, you would like to be just on time, right before the processor actually needs that data, it gets it. And maybe if the processor doesn't need it, you discard the data also, right? That's another way of managing, but it's not prefetching. It's like pushing the data, pushing useless data out, which we should do more, maybe, potentially, so that we can create space for something else. So when a data item is prefetched, it affects the timeliness of the prefetcher, clearly. And prefetcher can be made more timely by making it more aggressive. What does this mean? An aggressive prefetcher tries to stay far ahead of the processor's demands access stream. This could be done in hardware or software. In software, this may mean that your prefetch instructions are moved earlier in the code. We're going to see software prefetching briefly. Yeah. So for example, if you go back to the patterns that we looked at, the first pattern over here, a +1 stride. A very aggressive prefetcher may, for example, if it prefetch 32 addresses after a +4, right? Assuming a +1 stride. That's very aggressive because it's assuming that this will happen. It's consuming a lot of bandwidth, but it will be more timely. When the processor demands a +5, maybe it won't be timely. A +6, maybe it won't be so timely. But a +7, 8, 9, 10, 11, because you already sent those requests, maybe they will have completed by the time processor needs it. Of course, it depends on how fast the processor generates these requests as well. So it's not a simple equation in the end. Okay, so where has multiple dimensions? Where do you place the prefetch data? Do you place it in cache? Which is what most processors do today, because caches are huge today, and you don't want to add another buffer. So this design is simple. There's no need for separate buffers. The downside of putting a prefetch data into the cache is that it can evict useful data that's prefetched there by demands. This is called cache pollution induced by the prefetcher. And this may be not good, of course, clearly. Now, it turns out a lot of the data in caches are useless because a lot of the data is reused maybe once. A lot of the data is dead on arrival, actually. You cache it, but it's already touched in some level of the cache, higher level of the cache, that it's useless in the bigger cache, for example. So maybe this cache pollution is not that big, but you may get unlucky for sure, right? Some important data may get evicted. If you put in a separate prefetch buffer, you don't have that pollution problem. But now you have a much more complex memory system design. And our memory system designs are already very complex. Where do you put the prefetch buffer? Do you have a prefetch buffer for 10 of those prefetchers that we have, each of them? Not so good. How big is that prefetch buffer? Let me look at that. That's actually a big problem. If your prefetcher is really aggressive, that buffer needs to be almost as big as your cache. We have shown that actually in our feedback-directed prefetching paper in HPCA 2007, which is actually a form of it is implemented in essentially all processors today. If you don't have a large prefetch buffer, your prefetching cannot be aggressive. And if your prefetching is not aggressive, you don't gain a lot of performance. So it's better to put it in the cache. And there are other issues like when to access the prefetch buffer. Do you do it in parallel or serial with the cache? When do you move the data from the prefetch buffer to the cache, if ever you do? If you don't, then it becomes a cache plus prefetch buffer. And how do you keep the prefetch buffer coherent? Because some other application may actually need the same data and may write to the same data that's in your prefetch buffer, right? So this actually caused a lot of headache to the designers. As a result, many modern systems place prefetch data into the cache. Okay. Then the question is, which level of cache do you prefetch into, right? You prefetch from memory to L4, L3, L2, all of them, memory to L1, L2 to L3, L2 to L1, L4 to L1. So you have a lot of combinations clearly, right? Do you have separate prefetchers between levels? What are the advantages and disadvantages? It's good to think about it, right? L1 is, of course, very sensitive, as we have discussed in DDCA, for example. Whenever you're designing L1 caches, they're very tightly integrated into the pipeline. So the design decisions you make are actually design decisions that you make for the processor. So you should be very careful when you prefetch into L1. But you have more freedom in bigger caches, of course, right? And then the question is, okay, you decided to prefetch into some level, maybe all levels. Where do you place the prefetch data inside the cache, right? Do you treat the prefetch blocks the same as demand fetch blocks? Because they're not the same necessarily, right? So prefetch blocks are not known to be needed. So if you have, for example, least recently used management, a demand block is placed into the MRU position normally, most recently used. Of course, there are many different caching policies that people employ today. But normally with LRU, a basic vanilla LRU, a demand block that you know is needed by the processor is put into the most recently used position, assuming that it's going to be used again and again, so that it doesn't get evicted early. But you may not want to do that for prefetches, right? So do you skew the replacement policy such that it favors the demand fetch blocks? So when you prefetch a block, you put it in the least recently used position, for example. There are processors that did that. This is still not a good idea also because now prefetches may start evicting each other. So you have a lot of issues. So you need to be careful where you place the prefetch data. And in our paper that we're going to discuss in HPCA 2007, feedback-directed prefetching, we have an adaptive algorithm to decide where to prefetch based on the accuracy of the prefetcher. Okay, where doesn't end yet? Where do you place the hardware prefetcher in the memory hierarchy? What access patterns does the prefetcher see? Does it see all L1 hits and misses? Does it see L1 misses, L2 misses? And you can generalize this, of course. If you see a more complete access pattern from the prefetcher's perspective, maybe you can find out patterns better, right? You may get better accuracy and coverage. I defined accuracy. Coverage is basically how many of the cache misses do you actually cover, meaning do you prefetch? Different from accuracy. Accuracy is how many prefetches that you sent are actually useful. Coverage is based on all of the misses that you're trying to eliminate, what fraction of them are you actually eliminating, right? So if you actually have a more complete access pattern, if you see, for example, all of the accesses that L1 cache sees, now your prefetcher needs to be very fast, higher bandwidth. It needs to examine more requests. You may need to have more ports into the prefetcher. So a prefetcher becomes harder to design if it sees more. So there's a trade-off between potentially better accuracy versus design complexity, right? Okay, this is a picture that I used in DDCA at some point, but basically you can think of a caching hierarchy, but you can also have prefetching hierarchy, meaning prefetchers may exist at different levels. Good to think about that. Okay, so there's also hybrid main memory, if you remember an earlier lecture. Once you have this sort of memory, actually, prefetching becomes important. You have some slow memory, and you have some small but fast memory. You have some slow but large memory. And if you really want to take advantage of the fast speed of the fast memory, you may want to actually prefetch into the DRAM in this case, right? Fast memory. And there are actually a lot of works that do that. And this doesn't end here. Memory hierarchy today actually extends beyond the single server also. So you may actually have some local memory over here, which is very similar to what we have seen in the last two slides. But that memory may not be enough. And in many big applications and data centers today, what happens is you have remote memory, like there are memory nodes that store memory. This is also called disaggregated memory or remote memory. And you have some hopefully low latency network. And you actually have some data that's stored over there. And if you want to access that data, you'd better have a good prefetcher, because the latency to access that remote memory is not fast. So if you're interested, there's disaggregated memory, and this is an area that we have worked on. And there's actually a lot of benefits to this. This is a more system level design. Okay, I think this is a good place where I will stop. In the next lecture, we're going to start with how, basically. And we're going to cover different methods of doing prefetching, which is going to be fascinating, hopefully. And I will emphasize that there's a lot more room for innovation in all of these areas. That's why I hope if you have time, you would consider competing in the data prefetching championship that Rahul, Konstantinos, and I are organizing. Okay, have a good weekend. Stay warm.